Bonjour tout le monde. Good morning. On commence pas tout de suite, on va commencer dans 5 minutes. We'll start in something like 5 minutes. Je voudrais juste dire qu'en fait, à cause de la richesse de notre programme, il y a 2 manifestations ce matin. Vous êtes dans la bonne salle, mais il y a aussi quelque chose dans la salle Fatima Ferria, qui est là-haut. Et c'est l'atelier d'agriculture qui est animé par mon ami et collègue Bruno Gérard, mais restez ici, c'est ici que ça va se passer. Mais j'ai été obligé par l'organisation d'annoncer qu'il y avait aussi un débat dans la salle Fatima Ferria, où il fait extrêmement froid. Restez ici. Voilà. Donc on commence dans 2 ou 3 minutes. On est mercredi. Alors hier, je ne sais pas si vous étiez là dans la salle, ceux qui n'étaient pas là hier ont raté un débat assez extraordinaire. Entre 4h et 18h30, on a eu une conférence de Grégory Chaitin qui a commencé tout doucement, et qui nous a emmenés tout doucement vers le sommet de la réflexion mathématique et méta-mathématique avec Grégory Chaitin, et ensuite il y a eu Stephen Wolfram, David Chavallayas et Hervé Svirn qui ont rejoint Grégory. On a eu une discussion sur les bases philosophiques et métaphysiques presque, j'aime pas trop ce mot, les bases philosophiques et méta-mathématiques de la réflexion actuelle en mathématiques. Et je crois que c'était un grand moment. Je vous dis ça pour ceux qui n'étaient pas là hier. On enregistre en fait toutes les conférences, tous les débats sont enregistrés. Et donc je vous recommande, avant de regarder la conférence de Chaitin et le débat qui a suivi ensuite, d'aller au Health Center ici à Ben Guerir. Ils ont de l'aspirine. Vous devrez acheter de l'aspirine et ensuite vous regardez le débat entre Chaitin, Svirn, KAUFFMAN et Chavallayas. Alors, j'attends le feu vert de notre président bien-aimé pour commencer le débat, parce qu'on attend une délégation de très haut niveau qui va venir. Alors, ce matin, on a un programme également riche, en fait, très riche, avec Stuart KAUFFMAN. Je laisserai tout à l'heure Reda Benkiren présenter. On peut y aller? D'accord. On a donc, bon, je vais annoncer le programme, so I say a couple of words about what we are going to do this morning. On aura d'abord une conférence de Stuart KAUFFMAN. Alors Stuart KAUFFMAN est quelqu'un d'extrêmement intéressant, en ce sens qu'il s'intéresse à peu près à tous les domaines du savoir et de la science, sauf l'astrologie, donc j'ai bien vérifié ce matin, et il a des théories sur à peu près tout, ce qui convient en fait à un scientifique, et en plus c'est quelqu'un d'extrêmement sympathique. Donc Stuart KAUFFMAN, je laisserai tout à l'heure Reda le présenter, et sa conférence s'appelle The Inevitable Anthropocene and Our Choices Now. C'est vraiment très long comme titre. Et ensuite, on va faire un break. Puis ensuite, il y aura Ivar EKELAND qui va parler de climate change, transition, bifurcation or catastrophe. Et je dois dire que je suis assez ému de voir Ivar EKELAND à Ben Guerir. J'aurais jamais pu penser un jour, not even in my wildest dreams, de voir Ivar EKELAND. Je veux dire pourquoi. C'est que quand je faisais mes études d'économétrie en France, à l'école des mines de Paris, le premier livre que j'ai acheté avec ma bourse était un livre de mathématiques pour économistes de Ivar EKELAND. C'est là que j'ai appris à faire de la maximisation sous contrainte, des choses comme ça. Et donc tout à coup, il est là, à Ben Guerir, et je vais l'emmener tout à l'heure manger les fameuses brochettes de Ben Guerir, et c'est quand même très étonnant d'avoir mon héros intellectuel d'il y a 30 ans, tout à coup avec moi à Ben Guerir en train de manger des brochettes. Donc sera le deuxième orateur, et ensuite on aura Johan BOLLEN qui va parler de Toxic Networks. C'est d'ailleurs le livre qui est parti le plus vite de la librairie qui est là. Donc les étudiants ont le droit chacun de prendre un livre, et le premier livre qui a totalement disparu, c'est Toxic Networks de Johan BOLLEN. En tout cas, vous voyez que le programme est chargé, il faudra se concentrer. Je demande maintenant à mon ami et collègue Reda de venir. Alors je dois répondre à une question qui m'a été posée hier par mon ami Ali, le philosophe, qui m'a dit c'est un peu dommage parce qu'on a des gens extraordinaires, de très haut niveau, qui sont ici, mais on n'a pas pu leur poser de questions. En fait, c'est parce que le programme est tellement riche qu'on a été obligé de supprimer cette partie où il y a un dialogue entre la salle et les orateurs. Mais en fait, c'est pas vraiment problématique parce qu'ils sont là. Vous avez qu'à si vous montez une embuscade, il y a 3 personnes qui se mettent là, 2 personnes qui se mettent là, et vous laissez KAUFFMAN, EKELAND, BOLLEN, vous les laissez pas sortir. Vous pouvez les prendre en embuscade ici, et vous pouvez leur poser toutes les questions que vous voulez après leur talk. Et en plus, leurs livres sont là, donc vous pouvez aussi acheter ou pour les étudiants prendre leurs livres, et ça fait une sorte de dialogue. Voilà, je pense qu'on est prêt. We are ready now to start. Alors on me dit qu'il y a un jingle qui va passer, alors jingle.
Chaque zone de l'UM6P est équipée d'un plan d'évacuation qui indique les sorties de secours et les gestes à tenir en cas d'urgence. Prenez votre temps de l'observer ou demandez de l'accompagnement par le staff organisateur de l'événement. En cas d'écoute d'alarme, prendre du temps, ne pas se précipiter, suivre les équipiers d'évacuation ou le chemin le plus proche vers une sortie de secours indiquée par cette signalétique. Ne pas utiliser l'ascenseur. Une fois dehors, se déplacer vers le point de rassemblement pour confirmer votre sécurité au responsable d'évacuation et ne pas quitter le point de rassemblement qu'après autorisation. Si vous êtes le premier à notifier une situation d'urgence au sein des lieux de l'événement, vous devez activer le système d'alarme en poussant sur les déclencheurs manuels. Nos équipes sont à votre disposition et vous souhaitent un excellent événement.
Okay, thank you. I will ask now Stuart KAUFFMAN to join us and take the floor. And while you are doing this, Stuart, Reda Ben Kiran is going to say a couple of words about you.
Stand here at the moment.
Well, stand and be counted. No, you can sit, Stuart. You can sit here and then you can take the floor.
Bonjour à tous. Pour cette 3e journée, nous avons Stuart KAUFFMAN qui est avec nous. Alors c'est une grande joie parce que c'est vraiment qu'on parle beaucoup des sciences de la complexité. C'est un des fondateurs de ces sciences de la complexité dans le sens qu'il en a fait vraiment le design, le dessin, hein, voilà, l'esquisse, mais aussi l'intention de les travailler. Il est médecin de formation, il a été disciple, très proche, pas disciple, mais très proche du cybernéticien Warren McCulloch. Il a été aussi, avec son ami Brian Goodwin, un des biologistes qui se sont attachés à développer une réflexion théorique appliquée à d'autres disciplines. Chaque fois, j'ai une capacité à qualifier chacun de chacune de nos personnalités scientifiques, je dirais que Stuart KAUFFMAN a une capacité absolument phénoménale de conceptualiser. Donc, c'est quelqu'un qui a produit une œuvre conséquente. Je voudrais quand même citer ses titres pour que vous ayez une idée du parcours. Il a des métaphores très utiles, l'adjacent possible. La structure mythique, mythical structure, c'est une structure, c'est un concept que j'ai moi-même emprunté, l'idée que nous sommes habités par une structure mythique dans notre manière de voir et de penser le monde, et que des fois cette structure mythique peut nous encamisoler, et qu'il faut s'en libérer pour inventer, créer une nouvelle manière de voir. Il est l'auteur de The Origins of Order, Self-Organization and Selection in Evolution, At Home in the Universe, The Search for the Laws of Self-Organization and Complexity, Reinventing the Sacred, A New View of Science, Reason and Religion, and A World Beyond Physics, The Emergence and Evolution. Bref, nous avons l'occasion de l'écouter et n'hésitez pas aussi, s'il n'y a pas la possibilité pour les étudiants, c'est un point important de poser des questions. Nos personnalités sont là toute la semaine, n'hésitez pas à les mobiliser dans les halls, dans le coin de la librairie, à l'extérieur et ils seront tout à fait ravis de pouvoir échanger avec vous. À vous, Stuart. The floor is yours.
Bonjour, alors. I've been a scientist for about 60 years now. I'm deeply glad to be here. I think Mustafa, Hassim, Reda, there is a sense of possibility that's in the air. The English word is portent, that things may unfold from where we are now, that we can just begin to glimpse. And it's lovely. I think we should take seriously the confused sense of what's next possible. So I'm going to talk on the title, The Inevitable Anthropocene and Our Choices Now. Even more broadly, I want to talk about a prolegomenon to a next axial age. If this is right, it's civilizational. And that's the portent that is here. Next slide, please. Oh, I make the next slide, sorry. Okay. My friend Jan Dijkstrahuis made this lovely image of a falsely colored fungus growing on a root of a plant. The central message of what we're in front of is that we're of nature, we're not above nature. In Western science, we've thought we were above nature for hundreds of years, and we have to get beyond that, and I'll talk about that a lot. So let me tell you briefly about the first axial age. Between about 800 BC to 200 BC, in many, many different cultures, 2,500 years after writing was invented, and between the ancient and the new empires, independently around the globe in independent civilizations, somehow humanity moved beyond the god of the hunt in search of something higher. For Plato was the good, the true, and the beautiful. And in that period, we got Confucius, the Buddha, Jeremiah in the Old Testament, Plato, Socrates, Aristotle. It was a huge transformation in the way we are in the world, and all of our major religions derive from that era. Before I talk about this slide, I want to pause with where I was. I was realizing this morning, think for a moment of Francis Bacon in 1620 in Novum Organum, and he's moving us beyond Plato to modern science. The triumph of modern science is also its tragedy. The triumph of modern science is to master nature and gain control of it, and we have. At the same time, we're destroying the biosphere, and our own success has alienated us from the nature out of which we came. I think that we need to consider going back and being of nature. I'm going to talk about the adjacent possible in an equation that I wrote down, the TAP process. It carries implications for the cultural and the technological evolution across 2.6 million years. It's quite surprising, from Australopithecus to Cro-Magnon to China to us. And I'll just show you in a few slides. This is an amazing unifacial scraper from about 2.6 million years ago, from a young 16-year-old girl, Australopithecus. These are the exquisite pressure flake stone tools that Cro-Magnon had. This is the Great Wall of China. The first construction of it was around 700 BC to keep out the Mongolian hordes, and reassembled and reconstructed over later years. Notice the increasing complexity to now. That's Russian astronauts a few years ago on a spaceship. Just get the sense of the evolution from a few stones to where we are now. This is the equation in question. It's the only equation I've written in my life, and a whole large number of us are working on it. Let me explain it. I don't think I have a pointer, so I'll just use words. What I was thinking about a number of years ago, suppose that you have an economy at some time t that has mt things in it. I don't have a pointer, so you see mt. And I was wondering, how many things will you have in the next period? Well, you'll have the things that work now, but you might make new things out of what you have on hand. So that's this term to the right. And the idea is you can take one thing and reshape it, or you could take two things and combine them, like the printing press, which is a recombination of movable type, and a wine press. You could take four things. The Wright brothers airplane is a combination of a bicycle wheel, an airfoil, a propeller, and a light gas engine. So that expression MT with I written under it means MT choose I. So if MT is 40 and I is 1, you're asking how many things can I pick one at a time out of 40? And the answer is 40. If I is 2, it's how many pairs of things you can pick out of 40 things. And that's a very much larger number. And if it's 3, it's a still much larger number, and so on. So MT choose I goes up until MT is a half, then comes down. The symbol alpha is just meant to capture the idea that it gets harder and harder and harder to make something new. If you're trying to do it with 2 things, it's even harder if you're trying to do it with 10 things, and so on. So alpha I decreases in ways that you choose with I, and I is just the number of things. It's a very simple equation. It has just astonishing properties. Those are the people who worked on it. Wonderful Brian Arthur pointed out in The Nature of Technology, a wonderful book you should read, that technological evolution happens by recombination of things that are around. So does biological evolution. So TAP predicts 3 independent distributions: a hockey stick in the number of things, a hockey stick in the complexity of things, and strangely, a power law descent distribution for 3 million US patents. So this is led by Roger Koppel in constant dollar terms. This is per capita income for the last 2,000 years on good data. It will go back 20,000 years before that. So what you see is astonishing. Just look at it. Per capita GDP stayed stable globally for 2,000 years, and it started shooting up about 200 years ago. It's going up now almost vertically on a finite planet. So what? Well, this is the Anthropocene. This vast increase in wealth is simultaneously the Anthropocene. Now, does TAP bear on it? And the answer is it surely does. Here's our theory made into a slightly economic model. It has the property that for a long time nothing happens. It explodes upward faster than exponential. It reaches the continuous version, reaches infinity in a finite time, but has a pole. So the discrete process doesn't reach infinity, it just goes up faster and faster. So the TAP process is telling an increase in the number of things. What we think has happened is, over this time, the diversity of things made and traded has exploded. With the increasing diversity, there's increasing wealth, and that's what's driven the Anthropocene. So TAP actually is what's driven the Anthropocene, and that's why it's inevitable. It was bound to happen because of the TAP process. Meanwhile, if you reinterpret MT as the most complex thing made at time t. So if mt is 30, the most complex thing made at that time will have 30 parts. It predicts a slow increase, then a hockey stick explosion in both the number of things and increase in the complexity of things. So Australopithecus had about 10 similar stone tools. Cro-Magnon had a few hundred stone tools. If you don't know what an atlatl is, just look it up. It's pretty wonderful. But in the past 2 centuries, we've exploded to billions of different tools, and they range in complexity from knitting needle to the space station. They have. TAP is the first theory to begin to explain this. It may also explain in the evolution of life, probably does, the famous Cambrian explosion 550 million years ago, roughly 3 billion years after life started. This is a quite stunning slide. With patents, for every patent, legal patent, you can tell who its predecessors were. That's called the prior art. So for every patent, you can find out how its children and grandchildren are. And Sergi Valverde has now looked at 3 million patents from in the US Patent Office from 1870 to about 10 years ago. For every patent, he sees how many children, grandchildren, great-great-great-grandchildren you have. And most patents don't have many children, but some have a lot. So if you plot on the x-axis the number of descendants you have, so it's log descendants, and on the y-axis, logarithm of the number of patents who have that many descendants, you get a power law, straight line on a log plot's a power law. It's got a slope of minus 1.3. So it's true. The striking thing is that TAP does the same thing. The same equation is predicting 3 completely independent distributions. It also predicts the acceleration of the rate of technological change. Andrew Little has shown that every time you add a new item to the system, the waiting time for the next item is cut in half. And that basically says, why are we having an enormous speed up in the rate of technological evolution? Okay, now, that gives us the inevitable Anthropocene. And the inevitable Anthropocene was bound to happen, as Roger Koppel says. It started at least 300,000 years ago when we made the first compound tools of a flint attached to a staff with hafted to it with a thong to make the first spear. This means lots and lots of things. The juggernaut global economy. The economy is, the American word is juggernaut. It will just, our problem is, our global economy is amazing, it is powerful, it has momentum that is unbelievable to continue. It's growing at 3% a year, it will continue to grow at 3% a year. There's wonderful features. This growing economy has lifted millions of people from poverty, it's yielded better health, it's yielded better food, better education. The problem is we're on a finite planet. Think of that vertical curve going up of GDP. It can't keep going up vertically. It can't. It can't. It is the elephant in the room. It's a herd of elephants. The Anthropocene is driving the climate change we know about. It's driving the extinction events we know about. It's driving soil degradation. The fact that soil is degrading means that we're invading more and more habitats as we try to sustain output, and that's driving wave after wave of pandemics that are now roaming around us. We have a decade to 2 max to fix it. And the economy is a juggernaut and it's not going to want to get fixed. That's an existential problem. It's a civilizational problem and it's a global problem, and we're not talking about it. And I was listening to the wonderful people from the World Bank, and it's wonderful. But what about the fact that we're driving the Anthropocene while we try to sustain economic growth? We're going to have to do something different, and I'm hoping that Africa can do something different than the rest of the world has done. Okay, so I'm now going to switch to a topic that is, I think, unexpected. And I'm perfectly glad and delighted that there are physicist friends in the room. I may be saying something. This is with my friend Andrea Rolli. It is, one part is published, The World is Not a Theorem. The third transition in science is currently in press, Journal of the Royal Society interface out in a few months. It's surprising. See what you think, we may be wrong. So the question is what does it mean to surpass the Anthropocene? How do we get through it? My view is that we need two things. We need a spiritual transformation, and obviously we need a transformation of praxis, both enormous. I truly believe that the profound spiritual lesson is in this, the third transition, and it's really that we are above nature, not of nature. It's not Western science for the past 500 years wishing to dominate nature and control it. I will show you, I think, just convincingly, we never will, at least for the biosphere. We just have to give up a pretense we should never have had. Okay, so Joanna Xavier is a quite astonishing young woman. I am on 2 of her papers. This is her brilliant work. I happen to be the inventor of a theory 50 years ago that the emergence of life is the emergence of collectively autocatalytic sets. So a collectively autocatalytic set is I catalyze the formation of a second copy of you out of 2 parts of you. You catalyze the formation of a second copy of Bill out of 2 Bill parts, and Bill catalyzes a second copy of me out of 2 Stu parts. Joanna has stunned many of us who work in the origin of life field. She has looked at every prokaryote, 6,700 archaea and bacteria. They all have small molecule collectively autocatalytic sets with no polymers in them, no DNA, no RNA, no proteins. This overwhelmingly suggests that molecular reproduction arose in the early universe as a phase transition to molecular reproduction on planets with a sufficient diversity of chemicals. So the Murchison meteorite formed 5 billion years ago in the solar system, has hundreds of thousands of compounds on it, and experiments are underway to match the theory that says if we do that, we'll get the emergence of collectively autocatalytic sets, and that therefore the emergence of life's that expected phase transition in the evolution of the universe, which is going to be major for a lot of reasons. So, given an autocatalytic set, I wanted to find a Kantian whole. It's obviously Kant's ideas, and he was so stunningly brilliant. Gonan Ashkenazi in the Ben Gurion has made a 9-peptide collectively autocatalytic set. You see it drawn there with the little circles. So I'll say it, I'll simplify it as if it were a circle. Peptide 1 binds together 2 fragments of a second copy of peptide 2 and glues them together to make peptide 2. 2 does it for 3 and 3 for 4. So all of the peptides, each peptide makes a molecule that's the next type, and the whole set is a Kantian whole. Let me tell you what a Kantian whole is. This is a deep concept. Kant said an organized being has the property then that the parts exist for and by means of the whole. You're a Kantian whole. You have livers and kidneys and spleens. So you would not exist if you did not have a liver and a kidney or a spleen, but the liver and the kidney and the spleen exist because they're part of you and you have kids. So every living organism is a Kantian whole. This autocatalytic set is a Kantian whole. Each peptide is part of the collectivity of 9 peptides. The whole set reproduces by virtue of the catalytic activities of the peptides. So the parts, the peptides, exist for and by means of the whole. Fundamental idea. A rock is not a Kantian whole. A river is not a Kantian whole. A cloud is not a Kantian whole. Every living organism is. Now, I want to get to something. These are all important things. Steve Wolfram may be here this morning. We were debating whether he would be asleep. Because it allows us to define function. The function of your heart is to pump blood, but your heart makes heart sounds and it jiggles water in your pericardial sac. So this is crisp. It's a non-circular definition of function. The function of a part is that subset of its causal features that supports the whole. The function of the heart's pumping blood, not jiggling water in the pericardial sac. The function of one of those peptides is catalyzing the next reaction, not jiggling water in the Petri plate. Next step is fundamental. Selection acts at the level of the evolving whole, and it indirectly selects forever evolving parts. The parts are evolving to sustain the whole. That's why the heart has evolved to be better hearts. Therefore, selection is downward causation. Therefore, the explanatory arrows point upward, in complete contradiction to famous physicists Steven Weinberg and Kaku, who have claimed the explanatory arrows point downward and the causal processes point upwards. That may be okay for the abiotic universe. It's just false for evolving life. Fundamentally wrong. Okay, I'm going to get to the strangest thing and take time here. I'm doing fine. Andrea Rulli and I claim we have proven something astonishing. We cannot use set theory and all of the mathematics based on set theory to deduce the future evolution of the biosphere. There are physicists in the room, there's mathematicians in the room, and there's students in the room, and there's friends. See if we're wrong. But I'm going to take some time to unpack this because it's so unexpected. I'm not going to read the first paragraph. It says what I just said, and Andrea and I have done this together. So I'm going to say a sentence and then make good on it. It has to do with the unlistable, unordered, disappearing, unlistable, unordered, indefinite, and non-deducible different uses of things, like a screwdriver or an engine block, alone or with other things. When you think about it, it becomes obvious, but it's not what we talk about. So think about a screwdriver. So I'm going to ask a question. What can you do right here in Marrakesh today with the screwdriver? Well, you can screw in a screw. You can unscrew a screw. You can wedge a door closed. You can scrape putty off the window. You can break the window. You can stab somebody. You can put it on the window as an objet d'art. You can tie it to a stick and spear a fish. You can rent the stick to somebody for 5% of the fish catch. You can lean it against the wall, put a piece of plywood on it, and put a wet painting on it to keep it dry in the rain, blah, blah, blah. Notice the following things. These different uses are just different uses of things. It's a nominal scale. There's no ordering relationship between them. One is not greater than the other. So there's 4 scales: nominal, partial order, interval, and ratio scale. The uses of things are just they're unordered. So let me ask, how many uses of a screwdriver are there? I mean, for example, is there 7 uses of a screwdriver? Well, that's just nuts. Are there 43 uses of a screwdriver? Or is it an infinite number of uses of it? How would we know? The strange thing is the number of uses of a screwdriver is something like indefinite or unknown. And what's powerful about indefinite is that it does not map to the real line. Furthermore, given the use of a screwdriver to screw in a screw, you cannot deduce that you can use it to spear a fish. I'll come back to that better. And we can't list all the uses of a screwdriver alone with other things. It took me 7 years to get to an engine block. So an engine block is a piece of steel that's, you make an engine from it. It's about a half a meter long, a third of a meter wide, and a third of a meter deep, and you drill 8 holes in it. And that's how you make an engine. So it's an engine block. What can you do with an engine block? Well, you can drill the holes and make an engine, but Andrea is an Italian. He said you can store wine in the holes. The engine block is rigid, and you can use it as the chassis of a tractor. In fact, that's how tractors are made. With an enormous leap of imagination, I realized you really can use it as a paperweight. An engine, it's heavy, but it's a good paperweight. And then with an enormous jump, I realized the corners are sharp, and you can crack open a coconut. It's the same thing that we said about screwdrivers. Here I am using the engine block as a paperweight. Can I deduce from the fact that I am using this object as a paperweight that I can use this object to crack open coconuts? No, because this object might be a banana. So I cannot deduce one use from the other. The uses are unordered. I cannot list all of the uses. I can't deduce the different uses, and the number of uses is indefinite. And that's going to lead to the following. I can sort of read it. So I'm going to tell you about the axiom of extensionality in set theory. So Andrea and I were talking. I called him, I said, there's something strange about the axiom of choice in this stuff we're talking about. And we looked at This set theory is the foundation of all of mathematics, and it's got axioms. The first axiom is the axiom of extensionality. And it says two sets are identical if and only if they have the same members. Again, the axiom of extensionality says two sets are identical if and only if they have the same members. But I cannot prove that the uses of a screwdriver are identical to the uses of an engine block. I can prove that they're not identical because I can't list all the uses of a screwdriver, and I cannot list all the uses of an engine block. I cannot prove that the two uses are identical. That means we don't have the axiom of extensionality. That means we don't have set theory. Uses of things aren't sets. Furthermore, we don't have this weird axiom of choice. It's just wondrous, the axiom of choice. But the axiom of choice is identical to an axiom of well-ordering, but there's no ordering among the uses of things. So we don't have the axiom of choice. My mathematician friends, please hear it. I might be wrong, but we don't think so. So what does it mean? With no set theory, we don't have any numbers via Russell or Peano. So let's talk. Russell defines the number 1 as a set of all sets that have a single element. That would be the set of all objects that have a single use. Well, that's just nuts for things in the biosphere. Therefore, we can't define 0. 0 is a set of all things that have 0 elements, so we can't define 0. So we can't define 3. So we can't define 1 plus 3 is 4. So we can't get x plus 3 is equal to 11. We can't get equations. So we can't get quadratic equations. So we can't get the real line. We can't get square roots. We can't get imaginary numbers and complex numbers. We can't get spaces mathematically. We can't get vector spaces. We can't get manifolds. We can't get differential equations on manifolds. And because we don't have the axiom of choice, we can't integrate the equations of motion, so we can't even write. This is quite astonishing. What it means is we can use no mathematics. We can use no mathematics based on set theory to deduce the non-deducible different uses of objects that come to exist in the evolution of the biosphere or the economy. So I need to make this really clear. Evolution has in it something called Darwinian pre-adaptations, which are also called by Stephen Gould exaptations, where the same thing comes to be used for something else. I'll just tell you one example. Some fish have a swim bladder. The claim is that there were fish with lungs, lungfish. Some water got into some lungs. The same thing now, the lung is poised to become a swim bladder where the ratio of water to air tunes neutral buoyancy in the water column. A new function came to exist in the biosphere because the same thing came to be used for something else. The lens crystallins in your eye evolved from proteins that were enzymes. This kind of reuse of the same thing to do other things is all over evolution. It's why evolution is magical. So this is terribly important because of the following. If I give you a coin and I say top it, flip the coin 100 times, how often will it come up heads? And you say, I wonder what the probability is that it'll come up heads 43 times. You just wheel up the binomial theorem and calculate it. But you knew ahead of time all the possibilities. In the case of the adjacent possible of the biosphere, we don't know the sample space of the process. We don't know what is in the adjacent possible. So not only do we not know what will happen, we don't even know what can happen. This is an enormous step to take. We live our lives forward, as Kierkegaard said. We make sense of it afterwards. So I just want to raise for the physicists and philosophers in the room, Heisenberg's uncertainty principle demanded abandoning classical physics. If Andrea and I are right that we can not use mathematics based on set theory to deduce the evolution of the biosphere or the global economy, what does it mean for science? It means something big. We may be wrong, but we don't think so. So I want to focus on this one. I fell in love with this with Andrea about 1.5 years ago. Take it in. And the reason is that if you take it in and feel it, you won't look at the biosphere the same way ever again. So let's consider a bacterium evolving. It's a Kantian whole. And Andrea and I were talking to one another about 1 year ago, and we realized the following. Every one of the thousands of molecules in that cell stands ever ready to be co-opted for some unused causal feature that can be used in some new non-deducible function. Every molecule can get used for something else. But the myriad new uses must always be coordinated with one another because selection acts at the level of the Kantian whole. Just pause and hear it. Selection acts at the level of the whole bacterium. Molecules in the bacterium, in some environments, some molecule that used to, let's just talk about what a protein can do. It can absorb a photon, it can conduct an electron, it can bind a ligand, it can catalyze a reaction, it can vary a tension load, it can vary a compression load. A molecular motor can walk on the protein. Every molecule can be co-opted for something else, but those new uses have to be integrated because selection demands they be integrated because it acts on the level of the whole. That means that the biosphere is inventing things that we cannot say ahead of time because we can't deduce it, and it's doing it faster than we can. This means this is emergence, it's not engineering, and once you've got it, you won't look at evolving bacteria and think they're just bacteria. They're doing things none of us can even say. So evolution is a propagating construction that's not an entailed deduction. This means something huge. It means that there's no law, there's no rules, there's no axioms, there's no rules of inference. The biosphere constructs itself. It means the physicist's dream of a theory of everything is false. It may work for the abiotic world. It will not work for a universe that contains an evolving biosphere. And Steven Weinberg would have been, I don't know what. Mikhail Kaku is a superb cosmologist who talks about the God equation. It's not going to entail the becoming of a biosphere. What I'm telling you is you cannot reduce the evolution of the biosphere to physics. Once there's something that exists, you can try to figure out how it worked. And the same thing's true for the global economy. Okay, what are our choices now? The first is global soil regeneration. Well, this is what I'm going to talk about. I've gotten fascinated by global soil regeneration. This is an amazing place to talk about global soil regeneration. We were talking about it last night. Many people in this room know more about it than I do, but I will tell you some of what I know. I think we can begin to talk about laws and structures to form global creative commons for medicine, for farming in many areas that link us together as a planet. We can emerge as a planetary culture if we form the structures and the legal structures that invite us and enable us to do so. Global Creative Commons is a way. I think the Global Creative Commons can democratize wealth creation and make meaning rather than money. This is from my friend Jan Dijksterhuis. That is the mycelium of a couple of fungi with a lot of bacteria on it. For the mathematicians, they're called organisms. I said that with a certain wryness. I love this that Jan sent me. Worms, they've been co-evolving with one another for 500 million years. So worms crawl through the fungi and eat them. But the fungi aren't helpless. The fungi have involved a gun cell. And when a worm crawls nearby, the fungus shoots a small molecular harpoon into the fungus, penetrates the fungus, and penetrates the worm, and the fungus pulls itself inside of the worm and eats the worm from the inside. So this is a dead worm, lost to the fungus. You think they're not smart? They've evolved a molecular harpoon to harpoon passing worms. Okay, so I want to talk about global soil regeneration. This is a tiny, tiny sample of all of the things happening on global soil regeneration. It's quite astonishing. If it's true, it's brilliant. I want to tell you about it. What I think at this point is that it's worth taking very seriously, but skeptically. David Johnson is a man in southern New Mexico, and he's been doing this for around 12 years. He invented an aerated bioreactor. It costs about $110. It's about 1.5 meters across, 2 meters high. When you build it, you put cones in it, or tubes. You fill it with leaves, water it a little bit, and 3 days later, you take the tubes out so air gets in. I can't read my own writing. Just a second. So he incubated this for 12 months, and he gets out about 250 to 300 kilograms of compost. The ratio of fungi to bacteria is 3.8 to 1. And by metagenomic analysis, there are thousands of species of fungi and bacteria. Here are the claims. First, what do? You take this compost, about 200 grams, and you dilute it in about 20 to 30 liters of water and just stir it. Then you soak the plant seeds and you plant the wet seeds. It requires about 2 kilograms per hectare. This is just amazing. It takes 2 kilograms per hectare. Claims. It increases the yield on the order of 120 to 140%. So rather than getting 10 grams, you get 24 grams. He's done this on tilled and non-tilled soil. I'll tell you what we've done. Second claim is, again, stunning. Almost published, but online on his site. On fields for corn and wheat, you can reduce by 85% any need for fertilizer. That's astonishing if true. The most astonishing claim is that 1 hectare treated with this material sequesters 30 metric tons of carbon dioxide a year. I'll come back to that. So here's what my young colleagues and I, Jan Dijksterhuis in Holland, and I, and John Crawford and E-Blocks are doing. We are actually doing the experiments. It's pretty informal right now. It needs to be serious, but we're beginning. First question, can we soak the seeds, air dry them, and then use them? So we're trying that. Probably we can. That's crucial for practical uses of seeds, so that if you could do that and plant them later, you could, people could create the seeds and sell them. This is now the central thing. Can we demonstrate with statistical significant results for all major food crops? Can we do it, can we show that we get the yield that we need without fertilizers? I'm sorry. Can we get it without using fertilizers at all, or with fertilizers not using nitrates? We're going to need to replace phosphates and potassium. Can we show that this competes with fertilizers that use no nitrates? If we could, it's huge. The nitrates are what are eutrophying all of our waterways, and they're adding to the cost of fertilizers, which you all know much better than I do. So if we can get this to go, suppose that's true. Here's the dream, if we could show all of this. The hope is if it's true, could we show it in the next 2 years? So if that were true, the major hope is that we could increase the global yield at lower cost to farmers using Johnson's treated seeds sold to them at lower total cost because they don't have to buy expensive fertilizer, and the fertilizer companies are doing better. And because they're all using the treated seeds, it gets this material around the planet. We may need different composts in different areas of the planet, of course. We're trying something else that's fun. The root ball from a treated plant is about twice the mass of an untreated one, but the surface area is vastly larger. We're looking to see if the fungi and the bacteria on the roots come from and mirror those on the compost, not just the nascent soil. If that were to work, we could use the roots themselves, grown from treated seeds, and inoculate the soil. That would be an enormous help. So this could have a massive impact, meanwhile, on climate change. If it's really true that you can sequester 30 metric tons in a hectare, there are 2.5 billion hectares under cultivation, and I think I learned that 30 times 2.5 is 75 billion metric tons. We are emitting 39 billion metric tons. If this is true, to be tested, this would have massive impact on climate change while our governments are going around unable to do anything to stop what we're doing. Do I believe it? No. Am I skeptical? Yes. Do I think it's worth investigating? Absolutely. So that's what I wanted to tell you about that. These are lovely images that Jan has taken of the fungi growing on the roots that grew from plants treated with the compost, and his images are just amazing. Pretty? And for the physicists, do you think you could deduce the becoming of that from the Big Bang? If you think so, I don't think so. So I'm getting towards near the end. Think of soil. I mean, fungi and bacteria have been co-evolving with one another for 500 million years, and we've been here for 300,000. Think of soil as co-evolving multi-species Kantian wholes. And I'm now going to tell you what I think is the first deliberate experiment. Now, I haven't even said what the issue is. Evolving organisms create ever new possibilities with one another by which they get to exist. The global economy is doing that also. I'm actually earning a living getting up here lecturing to you. 500,000, not 500, 50,000 years ago, we'd have been out hunting aurochs. We wouldn't be sitting around eating popsicles. The evolving economy has created ways we can make livings without doing what we did 50,000. So is the global biosphere. It's made ways to get to exist with one another. But we can't deduce the new possibilities that come to exist. I'm falling in love with the idea that we can ask the biosphere, how do you create the new possibilities by which you get to exist with one another? We can't deduce what those new possibilities are going to be, but we can watch it happen. So here's the experiment. Okay, so here's the experiment. Jan and I are talking about doing this. We've got money for another experiment. I'm going to start with about 50 soil bacteria. Each one is DNA sequenced. I'm going to culture one bacterium species for a year. Then I'm going to co-culture 2. Then I'm going to co-culture 3, then 4, then 5, then 10, then 15, 20, 25, 30, 35, 40, 45, and 50. So I'm just increasing the diversity of species that are co-evolving with one another. They're going to create ways to get to exist with one another. Can I see it? Yes, because they will create mutations that create and seize the opportunities that come to exist. I can use metagenomic analysis once a month to sequence all of the bacteria to see what mutations have come to be. This is a doable experiment in the next year or two. Nobody's ever done it. So suppose we do that and we plot the number of mutations that accumulate as a function of the number of species. Well, it may be linear in the number of species. If one species has so many, 2 species has twice as many, 3 species 3 times as many, or so K. But it might be the second order in the number of species. It might depend upon the number of pairs of species or triplets of species. We haven't the faintest idea. If it's more than linear, the species are creating opportunities with one another, new niches, new ways to make a living, and they're seizing them by hierarchical variation and natural selection. I'm in love with the experiment. We can begin to ask new questions. How does a biosphere create new possibilities? And I think all of this implies something amazing. We should not ask a single species to do something, ask the community to solve the problem, and we've never asked it before. Meanwhile, I happen to have made a patent many years ago on making libraries of random DNA, RNA, and proteins, just billions of random genes. Mark Bolivier and I had the founding patent. It's an industry that's worth hundreds and hundreds of billions, and it's wonderful. We've started a company to try to apply the same thing now to COVID and to agriculture and human health. And I realized about 2 months ago, I have this co-evolving bacterial community. What happens if I use this technique that, as it turns out, I invented, to clone random genes, making random novel proteins every now and then into this colony? They'll have new proteins to work with. I think we could begin to discover at what rate, if we need to, can we positively mutate a bacterial community to solve problems? And then we have to be worried about putting new genes into the biosphere. It's an enormous portent for the future. This is going to transform agriculture. The part without the mutation is going to transform medicine. The whole thing may have enormous implications for agriculture. And my friend Sui Huang has come up with a phrase that's magical. He says, to mine the adjacent possible of the biosphere. Sui's right. Not by dominating it. We can't. We can participate in it. So I want to get to an end pretty quick. We need, if we think of Kantian wholes, there are nested Kantian holes. A bacterium is a Kantian hole. A eukaryotic cell is a second-order Kantian hole containing a mitochondria and chloroplasts that are first-order Kantian holes. A multicellular organism is a third-order Kantian hole containing eukaryotic cells that are second-order, blah, blah, blah. You and your gut microbiome are a fourth-order Kantian hole. My guess is that the entire biosphere is nested Kantian holes, and we haven't thought about it, and so is the global economy, nested Kantian holes. David also thinks in these directions, and my wife Kate does. If that's true, and we're talking about collective action on a planetary scale, what would that mean? So one thought is that we create a distributed peer learning network, part of a global Creative Commons, a global Kantian whole. So some of us are now trying to create this platform in part with Microsoft and wonderful John Crawford at University of Glasgow. The idea is to create a computational platform for farmers to own, store, and analyze, and share the data using modern computational tools, statistical and computational optimization tools. They can't even do a t-test. If we could extend this to global agriculture, to soil, we have ways to extend it now to medicine with my friend Lee Hood. We think for my company P4 Bios, my friends and I, we will transform modern medicine doing it. There's much more that can be done. We're just beginning to glimpse it. And it's obviously not just the few of us, it's just to get started. Now, suppose we can do this Creative Commons and farmers around the world have the wherewithal to try small experiments with one another to vary the compost that they're using, the fertilizers that they're using, and the ratios of phosphate and nitrogen and potassium, but to vary the crops they grow. Farmers are entrepreneurs and they try things. In the United States, in the Southwest where my wife and I live, corn, squash, and beans, the three sisters, have been used for 1,000 or more years. They are mutualists. The corn makes the sugar, the beans captures the nitrogen, and the squash provides the shades. They're mutualists that help one another. How many plants can help one another, and how many animals, by turfing the soil, can help the plants? We've destroyed it all with monoculture. We haven't the faintest idea. If we set up a global Creative Commons with respect to agriculture, and we have millions of people trying experiments and sharing the information with one another, we can, this word outsource is stupid. We can do something very different about how we do science together. We learn to do it collectively with practice on the ground, assembling it and sharing the information. I think that we can do it. We just have to get it underway in some way that is harnessable. But this democratizes wealth creation because three farmers in Bangladesh come up with a bright combination of plants that's another three sisters. They know it, they own it, and the money flows to them, not the giant corporations. So this democratizes wealth if we can do it. And it also is a sharing economy where telling the truth matters. There's no point in lying. We're full of a society now sucked into echo chambers by social media destroying the body politic. So this invents a new way to do distributed science. I think we can do it, and it is a pathway to a global way of coordinating with one another. So this really is something like, this is overbold. I'll try to say it the following way. I was thinking about it driving in. What is it that's underway? Francis Bacon in 1620 said, he didn't quite say it, but he said, put nature on the rack and rest our due. He didn't say it, but the meaning was for Western science, us. The glory of the last 5 centuries is find out how nature works and by God, control it. We're not going to control the biosphere. We can't deduce what it's going to do. We can't pre-state what it's going to do. We can participate with it. But to participate with it means we really are of nature, not above nature. And to borrow my friend Sui's wonderful phrase, it's not even that we want to mine the adjacent possible of the biosphere. We want to participate with it and learn how to use the enormous capacities of the biosphere to create. to create a lot of what we want to create. We don't, in a sense, we don't need more skyscrapers and we don't need more concrete. We need to come to know how the biosphere does it. It's been doing it for 4 billion years. It's overstated, obviously, but it's something like being in the world in a different way after 500 years of glorious Western science. So it's towards an eco-civilization. We need practicality, and I think, at least for me, the spiritual part is we really cannot dominate nature. We really are of nature, not above nature, and this is not what we've thought for hundreds of years. So there's a pathway, maybe. Thank you.
Stay here for 1 minute. I have 3 questions for you. Thank you, Stuart, for a very inspiring, very interesting talk. As you know, we cannot take questions from the audience for practical reasons, but I will again abuse my privilege as moderator to make 3 quick remarks. One of them is even a question. First of all, you quoted Francis Bacon, Novum Organum, to discard this idea that you should be master and owner of nature. Stuart, please, if you are in a French sitting, talk about Descartes. Yes, because actually Francis Bacon and Descartes was contemporary, and they said exactly the same thing. Yes, we did. We quote always Descartes in the Discours de la Méthode by saying, by science, he said, science, nous nous rendons comme maîtres et possesseurs de la nature. We have become master. C'est la même chose. C'est la même chose. Master and possessor of nature.
That's at an era in which the machine is dominating us, and it's before Newton gives us the world as a machine.
Absolutely.
And we've lived. In fact, I think it's so big. We've lived with the machine image at least since Copernicus.
Yes.
The world is a machine. If Andre and I are right, the biosphere is not a machine. It's not a machine. It constructs itself. It constructs its own expanding phase space. It can't be deduced. It's the end of the dominance of the machine image.
Yes, and Descartes wrote his famous sentence about to become master and possessor of nature by science is 1637, and Newton was born in 1642. Newton was not even born, that Descartes has already that idea. Well, yeah. The second observation is I've seen that you say something about élan vital.
Oui.
Well, as you know, the last French philosopher who was Henri Bergson. Was going to Henri Bergson.
Non, mais c'est ça, exactement.
Yes, but in France, Henri Bergson is kind of discredited. So,
no, I know.
You know. So
I'll defend him.
I admire you for trying to resuscitate Henri Bergson. That's what you're trying to do, right?
Yes,
in a way.
I think he would have been glad. So may I just speak about it briefly? There are 3 closures, autocatalytic. I actually do, it'll take a minute, but it's worth
1 minute.
Okay. There's a beautiful idea due to Matteo Mosio and Mael Monteville that I really want to convey. It's an exquisite ideal. The start is the following. What's work? It's force acting through a distance. Then Atkins says, no, work is more interesting. It's the constrained release of energy into a few degrees of freedom. So you're supposed to picture a cannon and a cannonball and powder. The cannon is the constraint and it's the boundary condition. And because it's there when the powder explodes, you don't get a spherical wave, and it propels the ball. And even I realized many years ago, at the Big Bang, there were no cannons. So if it takes constraints to make work, where do the constraints come from? And I didn't know how to solve it. Here's the idea that these guys had, and it's brilliant. I want work, so I need some non-equilibrium processes. I can just let me have 3 non-equilibrium processes, 1, 2, and 3, but I want to constrain them, 3 constraints, A, B, and C. Just pause and hear it. So I have 3 constraints, A, B, and C. A constrains the release of energy in process 1 to construct a B. B constrains the release of energy in process 2 to construct a C. C constrains the release of energy in process 3 to construct an A. Just take it in. Their brilliant idea is, in a constraint-closed system, the constraints constrain the release of energy that does the work to construct the constraints. An automobile doesn't construct its constraints. living cells do. An autokinetic set achieves constraint closure. And it's a stunning idea. Once you get it, you know, how could they have thought of it? It's so brilliant. And if you put together constraint closure, autocatalysis, I think that is élan vital.
Yes, that's a form of vitalism in a way. That's exactly that. Well, my first remark, we have very clever, distinguished mathematician in the room, so I will ask my question under their control, Chaitin, Ekeland, Wolfram. You said quite boldly that without the axiom of choice, there would be no mathematics.
No, I didn't say that.
You said that.
No,
you actually wrote it.
Oh, what I should say is, without set theory, without the axiom of extensionality, and without the axiom of choice,
yes.
and without the axiom of choice, put them together. Our claim is we can't do any mathematics based on set theory.
I'd love to hear Chaitin and Ekeland and Wolfram on that
No,
point.
I kind of thought they might have comments. Steve may be here. He said he was going to sleep this morning.
All right.
So I challenged him to be here and beat me.
Yeah, but they spotted Chaitin and Ekeland somewhere. Thank you very much.
Voilà.
Thank you very much, Stuart. Thank you. It was wonderful. Thank you. Alors j'ai le plaisir maintenant d'inviter Ivar EKELAND à nous rejoindre. Comme je l'ai dit ce matin, et je le répète pour ceux qui n'étaient pas ce matin, Ivar EKELAND est en fait un être humain. Il existe vraiment, parce que pour moi, pendant 30 ans, c'était juste un nom sur un livre de mathématiques pour économistes que j'avais beaucoup utilisé quand je faisais des études d'économétrie. Puis j'ai eu le plaisir de découvrir que Ivar EKELAND actually exists.
Hello.
Bienvenue.
So do you. So do you.
So do I.
Yeah.
Alors, nous poursuivons cette seconde séance avec des personnalités scientifiques absolument exceptionnelles. Ivar EKELAND est mathématicien, c'est un auteur d'ouvrages sur, vraiment sur le hasard, le chaos, c'est le chaos déterministe. Il a présidé l'université Paris-Dauphine. Alors, ce qui est intéressant, c'est que l'université Paris-Dauphine est née au lendemain de mai 68 avec l'université Vincennes comme deux universités expérimentales. Et Paris-Dauphine fut le foyer expérimental de mathématiciens qui se sont attaqués à des wicked problems liés au monde de l'économie et de la finance. C'était des thèmes qui n'étaient pas travaillés par les mathématiciens. Et au fil des décennies, Paris-Dauphine est devenue une université d'excellence sur les sciences de la décision et de l'organisation. Donc, grand plaisir de vous recevoir avec nous. Ivar EKELAND a aussi diversifié ses thèmes. Il a produit donc des ouvrages sur l'équilibre, les mathématiques du chaos. Et récemment, il s'est investi sur la question du changement climatique. Alors ça, c'est un point important. Il a conceptualisé un cours sur le changement climatique, qui est un cours qui est obligatoire à tous les étudiants de Paris-Dauphine. Il a produit aussi, il est co-auteur d'une bande dessinée, donc très sensibilisé sur la question le challenge du climat et comment exprimer les données scientifiques de manière à conscientiser les individus sur cette question cruciale. Donc aujourd'hui, on poursuit donc cette thématique de la relation à l'environnement, à la nature, avec son exposé. À vous, Ivar.
Merci beaucoup.
Merci. Thank you very much. It's the best part, you get the applause before having done the work. So now let me do the work, and I'm going to ask, so what is this? Yeah, green. So let's see if that works. It works. So I'm going to ask a simple question, but I'm going to set the stage for the question first. So let me set the stage. Look, this is a graph. This graph describes the temperatures for the past 50,000 years. I'm not going into questions about how do you do it and so on. This is scientifically done. It's in a general agreement. These are the temperatures of the past 50,000 years. And you can see the blue line are the mean temperatures. On the left, you see mean temperatures. The yellow line is the carbon dioxide. And what can you say about these lines? First remark, you can see there is some kind of stability. Something changes about 15,000 years ago, but you have some kind of stability. Certainly, you have some kind of stability in the past 10,000 years, right? Now, I'm going to zoom on the past 100 years. Now, I understand that some bright student that's in that class, in that room, in that university, 100 years, how much is it a part of 10,000 years? 1/10? 1/100th. So I'm going to look here at the 100th part on the right. So what do you see? You see here the last part between 1850 to 2020, poof, something happens. It's a shock. Here, this is the last 100 years, and you see something is happening. There's a shock. And remember, this is just the 100th part of the whole graph. Something is happening, mean temperatures are increasing, and it's not uniform. It's in France, it's more. So this is what you call a shock. Now, where does a shock come from? Well, did I miss that one? Yeah. So where does the shock come from? Well, you see, the shock comes from, and you see another graph. Now, these are the CO2 emissions for the past years, and you see that the CO2 emissions have increased. Why do they increase? They increase because we send up, you send up CO2, and this is our global fuel emissions. So there is no problem. We understand the thing, we know it comes from, you emit carbon, and suddenly, then the CO2 increases. Okay, that's well understood. Now, I'm drawing your attention to this graph because you see the CO2 concentration from pre-industrial levels, 280, has increased to about 400. Now, 400 parts per million, right? That's less than 1,000th. There is very little CO2. Try to figure out how much CO2 there is in this room. Very little. And we have increased, we have doubled, we have increased from 200 parts per million to 400. Not very much, shall we say. In a short time, not very much. Right? It is what we call a nudge. You push something a little bit. So what we have done is, in a short time, push something. So what have we done to whom? Well, we've done that to the Earth, the planetary system. Now, I'm not going to go into details. We all, I think no one in this room would disagree with the idea that the Earth is a complex system. This is complex, whatever your definition of complexity is, this is complex. Biology, physics, this is complex, period. I'm not going to elaborate on that. So the complex system, and what have we done to this complex system, which you don't understand fully? We have pushed it out of equilibrium. I mentioned to you that you had some kind of stability for the past 10,000 years. And now, in the 100th of a time, we've pushed it, we've increased from less 2,000 parts per million to 400 parts per million. It is, and you see this is, we've thrown it out of equilibrium. Now I'm not going to go into the details again. What is the equilibrium? The equilibrium relies on the fact that the Earth should send back, gets energy from the sun and has to send it back. If the Earth does not send the energy back to the sun, then what happens? It warms. Yeah, but if temperature constant, it means that it sends back the energy, and now we are perturbing that. We're perturbing the equilibrium. So this is the situation. We have a complex system, which we don't understand fully. And we have, on this system, we perturb the equilibrium. And now, here is my question. How does a complex system in equilibrium react when you put a small nudge? Now, remember what I mean. I'm going to stress two things. First thing, I'm saying something very general. I'm a mathematician, and a very strict mathematician. I don't understand the foundations of mathematics. I don't understand biology either, and I don't understand very much about physics, so I understand very little, so I'm going to say general things which will apply to the Earth. I mean, this is the beauty of mathematics, right? I'm not going to say anything particular. I'm going to say something general about systems. And the other thing I'm going to say is, it is a nudge. So my problem is not, if I take a hammer and go hammer this piano, we all understand that something bad will happen. It is not my question. My question is, you have a system which is in equilibrium, and I push it a little bit. Right? I push it. So this is my question. You have a complex system in equilibrium. You push it. You do something to it, not very much. What happens? Now I'm going to give you several answers. First answer, smooth transition. No big deal. Everything happens as before. Just a little increase. No big deal. So you see, you increase from 250 to 500 ppm. Mean temperatures will increase between 3 and 6 degrees C according to the distance you go. And then you say, smooth transition means no big deal. It's a quantitative change. Temperatures will increase. Fine. No, so that's what many people say. We'll have warmer summers. Well, they're already warmer. Perhaps warmer winters also. There will be no big deal. You see, we can adjust to higher temperatures, right? Fine. And there may be some good effects. More carbon dioxide in the atmosphere, better for plants to grow. Warm up certain things, well, you have all the regions of Siberia and so on going to be exploited, so there are some good things that will come out of it. Note, however, that this will already have some bad consequences. Something that's not usually known is that if you have certain combinations of temperature and humidity, they are lethal, meaning you stay out there. If you have 40 degrees C of temperature and 100% humidity, if you stay out there for 4 hours, you die. This already happens in certain countries like Costa Rica. And you find out that the number of days, continuous days, when such things will happen and so on, is going to increase. So, but this is the first answer, smooth transition, no big deal, temperature increases, fine. Small changes all over the place. A small nudge, small change. Very logical. And you see, it's honorable. If you want to win a Nobel Prize, you just argue like that. So let me describe you what the Nobel Prize of Economics in 2018 says. Well, the Nobel Prize in Economics says exactly that. Small nudge, small change. We are going to produce cars, but it's going to be more difficult to produce cars because if it's warmer, then people work. It's difficult more people to work, and you have to install air conditioning and so on, so it's going to be more expensive. And the result is you can be very clever, you can do good mathematics and so on, and the end result is here. You see, optimality, optimal, is at 3 degrees 5 in 2011. You find out that it is optimal to reach 3 degrees 0.5 of warming in 2011, and you get a Nobel Prize. So the question, of course, is, what does optimal mean? And do you believe that? I mean, I know not a single scientist that would agree with the fact that 3 degrees 5 is good in any way. I mean, only economists believe that. But it is the argument, small nudge, small change, and this happens also because you adjust to past data. So that's the first answer. The second answer, very classical, is the system will respond in a qualitative way. And this was pointed out already, I forgot to mention. This is well known in mathematics, and it goes back to Euler. Leonhard Euler, le prince des mathématiciens. So we're going back to, as I remember, to the 18th century. It's called the buckling, le flambage. The buckling is as follows. You have a beam, and you push on the beam. If you push, it's okay. And at some point, the beam, it buckles. You all understand that. So you see now, it's a qualitative change. You can see that it is buckled. It's a qualitative change. It's not quantitative anymore. It's qualitative. This is what we call a bifurcation. So this is a new type of response. You apply to the system, you get a qualitative change. So there's now a qualitative difference. The structure of the system changes. This change is continuous, right? Once you start buckling, the more you buckle, the more you push on it, the more it buckles. And if you stop pushing, you go beyond, then you go back to it, right? So it's a continuous change. And it is reversible. So now we have a qualitative change, but it's continuous and it's reversible. How does that apply to climate change? Well, you see here these pictures are taken from the IPCC. And you see, let's look, these are what has been observed up to now. And here you have the changes according to various scenarios. You all know that the Paris Agreement will imply, let me check what the next slide is, yes. The Paris Agreement is that we stick at 2,000 degrees C, or at best 1 degree 5. And you see already that there are some qualitative changes. For instance, if you look at the Arctic, you're beyond 7 degrees. The Arctic is going to be beyond 7 degrees. Well, who can believe that? And now look at here. This will mean some qualitative changes. I'm thinking for some qualitative changes. And for instance, if you look at the next slide, look at this. Precipitations. Look at, you're interested in the middle one. So look what happens around here. It happens that you have precipitations inside Africa and the coast, including Morocco, no precipitation. And around the Mediterranean, you go going, and in the Mediterranean, you know, look up at the Mediterranean at 4 degrees, southern France, Algeria, and so on. Then you have the dryness. You have less than 1/2 precipitation. Excuse me, this will be a qualitative change. It's not the same, right? So these are qualitative changes. And in many ways, for instance, you see l'anticyclone des Açores, all these things. All these are going to changes, and fine. If you're interested, and you're students, you should be interested in that, you go to the website of the IPCC. Oh, yeah, here, this is, you go to the website of the IPCC, and the website of the IPCC, you can adjust to get this kind of pictures. There's an interactive atlas. So you go to the website of the IPCC, there's an interactive atlas. If you're interested in a particular part of the world, you plug in the thing, you get the precipitation, so on and so forth. So this is the second type of response, a qualitative change. Now, perhaps one could say, also qualitative. Think, for instance, of the effect of COVID. COVID is a small nudge, but induced a qualitative change. That's the second response. Now there's third response, and everyone has some intellectual heroes. Well, I'm glad to see that I am it for some very indulgent people, but I have my own. Here is René Thom. René Thom is a great mathematician who was born about 100 years ago. He died in 2002. And he was a very nice person, and certainly as a mathematician, my mentor. And part of his mathematical work, he translated it to some practical things which were very successful at the time, which is called catastrophe theory. Now let me talk to you about catastrophe theory. First of all, let me show you how good I am at computer science, manipulating, making drawings and so on. I'm fantastic at that. So this is what I do. I draw pictures by hand and I copy them. So I want you to look at this. I want you to look at this. You have different shapes, 1, 2, 3, 4, 5, 6, 7, 8, and you move from one to the other continuously. This is what the drawing here says. It says you move, c'est comme un curseur ou un rhéostat. You move, as you move along this curve, you go from 1, 2, 3, 4, 5, 6, 7. Think of it as a kind of button. You can move, if you go around like that, you go from 1 to 7, changing continuously, and you can move back, and you go up, and you can move all the way, you do whatever, and you change the shape. Do you change the shape in a dramatic way? No, it's continuous, right? You all understand this? It's important, right? You can see that my idea is you move around from one to, as you move around, the shape changes, and you can move back and forth, you do whatever you want. Nothing fancy. Clear? Clear. So now let me do something. I'm going to put a little ball on the bottom of number 1. So this is what you get. Now we're going to physics. This is called a potential well. This describes equilibrium. The little ball downstairs is in equilibrium. In physics, it's a potential. It is there. It's not going to move. If you should push it with, it's just there. Right? So this is a system in equilibrium. And now I move. From 1 to 2, what happens to the ball? Not much. 2 to 3, what happens to the ball? You see, it begins to be suspicious, but those things are happening elsewhere. But the ball doesn't know. You know, these are limited people. They look around them. 3 to 4, things still happen somewhere else, but it's elsewhere. Number 5, things are happening elsewhere, but they're happening elsewhere. And then suddenly here, what happens? Puff, the ball falls down. And this is very interesting. Again, it is general. It's not restricted to that. So this means, so what happened here? Did I make a big change in moving the thing? No. Did something, I made from, when you go here, you see it's very sensitive. If you cross the threshold here, a very small change will induce a very large displacement. So just moving a little bit, you see, the nudge. If the nudge is there, and you see we're increasing regularly the number, the CO2 of the atmosphere, we're moving around the curve like that. It could happen that at some point, the whole system just goes elsewhere. Not nearby. There are two things here. One is there's no warning. You have increased You have moved continuously, no warning sign. And the other thing is, you don't stay close. You move completely elsewhere. Just go somewhere else. Clear to everyone? So this is the first thing. That is what they call the catastrophe. But now let's have some fun. Let's move back. Let's go the thing the other way. Okay? Move back. So I'm moving back. Now I'm putting a little red ball where the other was. And I'm going the other way. So we're here. Now 7 is 1. I'm moving. From where does the red ball go? At point 2, it's still down there. Now, at point 3, the little red ball is not going to climb up. It just stays there. The green ball, here you see the green ball was here, but the red ball is there. There's no going back. It's not going back to original equilibrium, meaning if you reverse the thing, if you take back the carbon from the atmosphere, then it will not go back where it was. The new equilibrium is stable. If you really want the red ball to go back to the equilibrium, you have to go there, up, and here it will, and here it will go back. It's very far away. So, which means that the threshold here is one way. So, I mean, if you look at that, if you're interested, I think this, if you want to hear it from René Thom itself, you can look at it in my bande dessinée, my comic strip, and you will see it. I understand it will be in the library soon, but you see, this is exactly what I say, and here René Thom is explaining to you that at some point it goes down. So that's what the catastrophe is. So again, it's very general about systems. Don't believe that if you make small continuous changes, the system will respond continuously. Not true. A small nudge may cause a catastrophic change. The system goes from one equilibrium to another one, which is far away. The change is irreversible. Oh, I made a mistake. Let's go back. No, man. We go back. Now the new equilibrium is stable. And there is hysteresis. Hysteresis means the following thing. Let me go back. If you are in situation 4, I'm telling you, this is the concentration of CO2 in the atmosphere, whichever. I tell you, you're in situation 4. You're not going to be able to say in which state the system is, because it depends on past history. Do you come from 7, or do you come from 1? Now, is it relevant to climate change? Well, climatologists have warned us for a long time that they are what they called planetary thresholds. The planetary threshold is a situation where which is extremely sensitive to certain parameters. So these situations. So this situation, for instance, you had them. One is of interest to you. Certainly one is of interest to you. You had the West African monsoon shift, Sahara greening. You noticed that in the raining, that in the slides I showed you, there could be a lot of rain around the Sahara, but there may be a shift in the West African monsoon. There may be multi-stability in the monsoon cloud. West African monsoon shift, in good language, it means it stops. Period. No more monsoon in West Africa. So what does it mean, a planetary threshold? It's a situation let me describe it in detail, the one I know better, which is the Atlantic deep water formation. So I'm going to explain exactly what it means. So this is a planetary threshold. Now, Europe, so here is Norway, for instance. You see Norway, in Norway over here, the coast is never iced. No ice on the coast. If you go the other way, you see, no ice on the coast of Norway, mild things here, and if you go at the same latitude, you end in Labrador, and you can see the difference. So why is there no ice on the coast of Norway? Because of the Norwegian current. The Norwegian current comes from a North Atlantic current. It is what we call in French the Gulf Stream. And the Gulf Stream is basically taking hot water from the West Indies, les Antilles, and bringing it all the way up north. Fine. So you see, it's an escalator. You take the water here, it's warm, and you bring it here, and it goes along the way. But, I mean, water is incompressible, so it has to come back. How does it come back? It sinks, comes back, and goes up. So it's an escalator. And this is described here. Up, hot. Here, it sinks, and then you have the blue current, which is deep underneath, and goes back. Why does it sink? It sinks, not clearly understood, but it's a question of difference of density. And the density depends on many things, temperature, salinity, and so on, and very sensitive to that. Well, we have no control about these parameters. And you know, when you talk about density of water, you know, it's not going to double anything. You're really talking about very, very small things. And this could stop. And we're now seeing some weakening of that. Has it stopped in the past? Yes. So it is a planetary threshold. This thing could stop because it depends on very small parameters we have no control of. And if it stops, well, no more warming of the Norwegian coast, no more warming of Great Britain, no more warming of the West Europe, and then consequences that you have to figure out. This is a planetary threshold. Now we have, I described to you, 3 answers that a complex system can have to small changes. Has anyone a guess for a 4th answer? Well, the classical answer that all managers know, I mean, this you learn from managing institutions and so on, the unexpected. You just didn't figure out that this would happen. So let me tell you a story. A story coming from Snorri Sturluson, the saga of Harald Haraldsson, 2030, and I took it over in my book on Au Hasard. So the story is as follows. We are in the year 1000, and the king of Norway and Sweden are fighting over a certain city. And the Vikings at that time, they were civilized people, and instead of fighting, which is now the standard way of doing things, they say, it's not worth killing so many people, let's draw lots. And they decide, we shall throw lots. So the king of Sweden, the king of Norway meet, the king of Sweden throws 2 6s. He says to the king of Norway, thank you, no point of your throwing. Come on, says the king of Norway. 2 6s. Okay, very surprised. So we do it again. So the king of Sweden throws 2 6s again. He said, God is with me, clearly, let's part as friends. I wouldn't want to offend you. Don't throw your dice again. Well, says the king of Norway, there are still 2 6s in the dices, and God my Lord would not forsake me in this extremity. He throws the dices, and one of the dice breaks. And when it breaks, it shows a 6 and a 1. So he makes 13, and he wins. This is the unexpected, right? And this happens all the time. This is the thing you had not envisioned. And this happens, right? And in more recent times, you have the famous Rumsfeld classification. Rumsfeld, who was Secretary of State during the Iraq invasion, and not my favorite politician, but he said something very memorable. He says that there are several things when you make decisions. There are things you know. Okay, now a basic fact, which is always pointed out even by Spinoza. Spinoza pointed out explicitly, if you know that you know. Very remarkable. If you know that you know. Fine. But a thing you don't know. Aha. For a thing you don't know is very different. There are things you don't know. Planetary threshold. I'm telling you about things could happen, and I tell you I don't know. Yes, but I know I don't know. But there are things you don't know that you don't know. Right? When you throw that, you don't know that it might break. And it is very important. Some things, you have to realize that there are things that you don't know. It's very ambitious to think you know everything, or that you see, you must understand, I think, you don't know. And for instance, for me, I think personally, it is impossible to know everything about a living being, and especially about the planet Earth. I just think it's not possible. And there are things that it's not only that you don't know, but you don't know that you don't know them. You just don't know. So I wish to draw your attention in that framework, thing you don't know. Well, this was, is it applicable to climate change? Well, already in 1987, there's a very good famous article in Nature by someone called Broker, which is called Unpleasant Surprises in the Greenhouse. So it's 87. It was 1 year before the first IPCC report. And you can read the paper. And I'm just pointing out the thing. He's pointing out that there's so much we don't know. And his basic conclusion is, we play Russian roulette with the climate, and no one knows what is in the active chamber of the gun. 1987, published in Nature. And that is a reminder, we don't know. I think we don't know. So that's the fourth answer. So what is to be done? Well, fortunately, there is much to be done, right? And people here are trying to do a lot. But this is part of the difficulty, you see, because we have a complex problem, and if you expect a simple answer to a complex problem, you're wrong. The answer somehow has to be complex. It has to be complex. So let's see what the future holds for us. Well, So let me remind you the Paris Agreement says we should limit global warming to 2 degrees C and preferably 1 degree 5. Okay, I mean, this statement carries as much legitimacy as any statement anyone has made, because it's a consensus, it's voted by the states, and so on. Someone mentioned yesterday about some sincerity of intent. There was an Arabic word for that. Is there sincerity of intent around that? I don't know. But this is as legitimate a statement as anyone has made in this world. And it's supported by growing anxiety in the developed world, especially among the younger generation. So how do we do it? Yeah, that's what I told you. The answer itself has to be complex. So what should we do? So lots of suggestions around. The economist says, let's have a carbon tax. The engineer says, let's have a carbon-free process of production. The economist says, let's customize fertilizers. Municipalities, let's restructure urban transportation. But it is a complex problem. The answer is complex. There is no silver bullet. Not one of them will do. We have to do everything together. And this is what makes the thing exciting. It's exciting because everyone is involved. You see? No single thing will do it. People come to you and say, this will solve our problem. No. It is complex, and it's because of that that it is interesting. You involve everyone. You involve the young, you involve the old, you involve the engineer, you involve the economist, and so on. And you see, my personal point is that future education research should take this new perspective into account. We've been thinking up to now into educating students in math, doing research in math, or in sociology, or whichever. I think we should break these barriers, right? So that everyone, it's a common challenge, and people should be trained to work together to realize a challenge and to work together towards solving these problems. And I personally, when at Dauphine, at Dauphine, we've been trying to do that, creating this course for students, which is compulsory for students, and I am very impressed by what UM6P is doing in that direction as well, and OCP. I mean, this is really, in my mind, the future of education and the future of research. There is this idea that is complex, and everyone has to be together to build this new thing, which is a new world and a new society as well. And so this means change research, train researchers, train students, but also be humble. Be humble. We're not going to know everything. It's just not possible. Think of it. And especially in chaotic times such as that. And so, there are many situations in life when you don't know everything. I meet a stranger, I don't know anything about him. But there are things that you do and that you don't do. There are rules. There are rules of common behavior, of common decency and society. And these rules enable us to work in very uncertain situations with people we don't know. And so these rules are developed in law. This is called the precautionary principle. This is enshrined in the French Constitution, for instance. It basically says, when you don't know, don't do it. And also I believe it's important for personal ethics. You see, the example of Greta Thunberg, I think, is very striking, because if you believe in something, you have to show it. And you can do it in certain institutions. In my own university, for instance, the labs get penalized for using for flying. So I think they're very nice times. I will leave you at that. I will just end by a poetry that you know very well, and that will translate into French. You know that poetry. Personne n'est une île entièrement contenue dans elle-même. Chaque personne est un morceau d'un continent et un morceau du tout. Si une motte de terre a été emportée par la mer, c'est une perte pour l'Europe, comme si c'était un promontoire tout entier. Et si la maison de ton ami est emportée, c'est comme si c'était la tienne. La mort de toute personne me diminue parce que je suis impliqué dans l'humanité. Et c'est pourquoi ne va jamais demander pour qui sonne le glas, il sonne pour toi. Thank you.
you. Thank you, Professor Ekeland, and thank you for finishing with this beautiful poem by John Donne, Never send for whom the bell tolls, it tolls for thee. I have only one question. You started with the premise that the Earth is more or less in equilibrium, and that give it a nudge, give it a shock, what happens, etc. My question to you is, has actually the Earth ever been in equilibrium? Because you have solar radiation, which has fluctuated, you have the ice ages, you have that strange Milankovitch orbital change in the orbital of the Earth. So basically, the Earth has never really been in equilibrium, but you started with the premise that it is in equilibrium. So,
Yes.
you can use this one, I think.
Yes, these are questions of scale, right? So what I'm pointing, so for instance, it's well known that the astronomy influences the thing, but these work on a scale of like 50,000 years, right? You have other factors. So all equilibria are temporary, especially in this world. You know, my body is in equilibrium. Oh yeah, I mean, I'm in equilibrium because I maintain about 37 degrees. This is fine. One day this equilibrium will end. So these are temporary, and this is why I began in this way. I'm saying that for the past 10,000 years at last, things have been stable. So this is what I meant at the present time. And many people are attributing to that fact that civilization developed at that time. And things on an unprecedented scale now, things are changing on a scale of 100th. I pointed out that 1 century is 100th of that period. And they're changing very fast. It's really a shock now. So when I talked about equilibrium, I was thinking of a situation that had been around for the past 10,000 years.
Okay, thank you very much. It's now very clear. Merci, Professeur Ekeland. Bien, je crois qu'on va passer... Ah oui, je crois que ça mérite aussi applaudissements. C'est vraiment très intéressant. Je crois qu'on va passer directement au troisième et dernier orateur, parce qu'on a pris un peu de retard. Donc c'est la dernière conférence de ce matin. C'est Johan BOLLEN qui va nous parler de Toxic Data. Et je laisse mon collègue et ami Reda Benkiren présenter Johan pendant que Johan arrive.
Yes, Johan BOLLEN is a psychologist. He did his PhD at the Free University of Brussels. This place is a very important place regarding the studies of complexity, emergence, nonlinearity, because this school was founded by Ilya Prigozhin, who was a Nobel Prize, and Johan BOLLEN was a student of Luc Steele's, a thinker of artificial intelligence, who did a brilliant presentation yesterday, and he was also, his thesis was done with Francis Eiligen, the cybernetician from the same university that will be here tomorrow on a session on self-organization and emergence. So what is very interesting with Johan BOLLEN, he has also worked for the Los Alamos National Laboratory in the US. He's professor at Indiana University. He has also participated to a very interesting documentary film done by the Santa Fe Institute titled Solutions. We here focus more on wicked problems, but I suggest that this documentary film is available on the web, and it's very interesting exercise. And Johan BOLLEN is also, I think his talk will be listened by the young students, because he's proposing, we mentioned the notion of precautionary principle. So regarding the digital network, the social or unsocial network, he will talk about the potential dangers of this new environment. Thank you very much. You have the floor.
Okay, great. Let me advance the slides. I want to apologize in advance because I think this is the previous presentations were very uplifting, very optimistic, very happy, nice messages, poetry, etc. And I have something to offer that is a little darker, I think, but equally relevant, I hope, to this audience. So the title of my talk is a little bit of a play of words with one of the other presenters who published a book on toxic data. And so I figured to call the presentation Toxic Networks, because I think that's more or less, that's a pretty good summary of the environment that we find ourselves in right now. We live in a world of complex systems. Very often these systems are amenable to be modeled by complex networks. Complex networks are a fantastic mathematical device by which we can study the topology and the structure of these complex systems, which essentially consist of large numbers of entities that interact in a non-trivial manner. Now, the complex networks are generally distinguished by a number of characteristics which are not trivial at all. For example, a heavy tail in the degree distribution, which generally could be interpreted as saying that some nodes in the network have many more, very few have very many connections, and most nodes have very few connections. So there's a strong inequality of connectedness in these networks. A high clustering coefficient, meaning that nodes tend to cluster together in tightly packed assemblies. There could be a strong sense of assortativity or disassortativity among the vertices, which means that the vertices that have similar features tend to cluster together. We see this in social networks, for example, where people prefer to connect to other people that are like them in terms of religion, race, sex, etc. Community structure and hierarchical structures. These networks are everywhere, and I think the study of these networks has gotten a big boost in the past 20 years because of the emergence of the internet, which in many ways could be considered a complex network of both people and machines connected across geographic, linguistic boundaries. For anyone interested in sort of this still evolving science of networks or network science, I highly recommend Barabashi's book on network science, which provides a really a fabulous introduction to this domain. Now, I will say I started work with Francis Heiling as his doctoral student in the early 90s when Francis's project, the Principia Cybernetica, had just created the first Belgian website. So that's a little bit of a claim to fame, you know, world famous in Belgium, as they say. And we were really smitten by this technology because it became obvious to us that this was going to be a technology that was going to connect potentially billions of individuals across geographical, linguistic, cultural boundaries. And very soon we started to look at sort of the future of this kind of a network as something that would unleash the potential of humanity, right? In terms of creating almost like a global brain where each of us individually would be a neuron, and the axons that connect us would be provided by the internet. So we'd have a giant network that we were conceiving of as a global brain. And I'm referring to a paper here by Simon Dedeo, which has done quite a bit of research in showing that some of the phenomena that we see, the collective phenomena, the behavior that we're seeing in these kind of networks do actually represent a form of computation that is quite non-trivial. To some degree, sort of this was a utopian view of this future of the internet, the future of society that would make use of the internet. We were thinking about sort of something that would liberate humanity and de-intermediate societies, meaning that existing structures which mediated between the individual and a variety of institutions and social goods, that they would disappear, and there would be a very direct form of communication and access to information, but also to goods, which to a degree has happened. But over the past 10 or 15 years, I have to be honest, I've been thinking of revisiting that utopian vision a little bit. What we've seen over the past 10 or 15 years is sort of a de-intermediation. If you look at, for example, the internet right now, about 60% of the world's population has access to the internet, uses the internet. About 60% of the entire world, about 5 billion people, uses some social media platform. In fact, 57% of network traffic right now is caused by big tech. Google, Netflix, Facebook, Apple, Amazon, Microsoft, just a few companies that are essentially causing the overwhelming majority of network traffic on the internet, meaning that the internet was, has been very, sort of the flow of information has been very strongly concentrated in the hands of a few corporate entities. And so over the past 10 years, again, we've seen some phenomena that are very worrisome. Instead of sort of a wisdom of the crowd effect, sort of this global brain that would lead to the emergence of an intelligence that would allow us to solve these really complex problems, what we've seen is somewhat of the opposite, the sort of Charles Mackay vision of the madness of the crowd. We've seen spread of misinformation, polarization, widespread distraction, extremism, ethical challenges, and also implications for the mental health. And I'll go into that a little bit because I think that social media and the internet is actually implicated in some of the recent phenomena that we are observing in our youth. If you're interested in reading something really interesting about sort of a criticism of social media and its widespread use in our population, please read Jaron Lanier's book, 10 Arguments for Deleting Your Social Media Accounts Right Now. It's a very short and sweet read, and also very informative by someone, a true visionary who really understands these environments better than many of us do. But here's something I wanted to point out, and it's, I'm looking at this from the side, but here's something. These are statistics about American youth, and I grew up in the 80s and 90s. This is the height of the summer of love, the emergence of acid house, the raves. It was a pretty wild time, good times. Today's youth is much nicer than we were. They use less drugs, they smoke less cigarettes. They have less sex, they watch television less. So when it comes to sort of the vices that characterized, if I could say that, my generation and how we spend our youth, today's youth are good. They're not naughty, they're nice. But at the same time, if you look at the graphs at the bottom, this is based on the Youth Risk Behavior Survey, you can see that has not led to increases in well-being. I mean, these are disastrous statistics. I mean, I cannot stress this enough. I mean, if you look at recent data, you could see that about 1/3 of teenage girls right now reports having either contemplated or effectively planned suicide. I mean, the mental health of our youth is in a very precarious situation. And the one thing that is remarkable about this generation is that although they are very nice in terms of their sexual behavior, their alcohol consumption, their drug consumption, etc., the one thing that distinguishes them is the prevalence of the use of smartphones, tablets, particularly the use of mobile devices on which they access social media. And so it's natural to think that perhaps the internet and social media environments are actually implicated in this odd paradox that we observe. And when it comes to what we've seen in the past couple of years with the COVID-19 pandemic, of course, that has done no good. These lockdowns have been quite disastrous for our mental health. And as you can see from these statistics, again, these are US adults. So they're in a little better shape than US youth. But as you can see, 11% seriously considered suicide, 31% exhibits the symptoms of anxiety and depression, which are very debilitating disorders. And those are the adults. But for the youth, the challenges are even more significant. And I cannot stress how disastrous these reports are. They reveal a truth about our youth that we have to face, and that we have to understand the reasons for. Anyway, so the thing is that if you look at the numbers, I don't know whether I can go back to the previous slide. So more than 40% of high school students in the United States are feeling so sad and hopeless that they cannot engage in regular activities. If you compare that with sort of the overall prevalence of, for example, anxiety and depression, which is the leading contributor to the burden of disability worldwide, according to the WHO. The lifetime prevalence of depression is 16.2% across the population, depends on gender, etc. But as you can see, this is much better than what we're finding for our youth right now. Again, the same people who use drugs less, drink less alcohol, smoke less, have sex less, watch television less, but are very heavy social media users. And so this made me think a little bit of a paradox that we might observe here. So social media use is nearly universal among the, not just among the youth population, but also among young adults and our youth. These lockdowns, the social isolation that marked them, led to more social media use. But social media use, don't forget, is specifically geared towards connecting people, to form social connections. We see all of the tokens of, of social connectedness. Friends, follows, likes, etc. These are all sort of, simulations of social connections that we as a social species really crave and need for our well-being. And so, but here's the paradox then. You have so many people using social media, which means they can establish many social connections, many more than used to be possible, but at the same time we have we seem to have a disastrous effect on well-being. And I don't think it's still up in the air somewhat. There's been quite a bit of research, even controlled experiments with people who were effectively paid to not use social media for a month, and where we saw increases in their well-being. And there's been quite a bit of sort of survey studies that show that overall time spent on social media is strongly associated with internalizing disorders such as anxiety and depression and lowered well-being. So this is sort of a paradox, if you will. Social media helps us to make connections. As a social species, we need connections, but then it seems to be associated with lowered well-being. And so there's really been accumulating evidence of the role of social media and social networking in lowering well-being and the prevalence of internalizing disorders such as depression and anxiety. So that's a very dark picture. So but what's going on here? How could we possibly understand this? So if you look at these social networks, they're really interacting with people whose behavior, affect, and cognition is very strongly interrelated. It's a complex system where our cognition, our cognitive state affects our affect and our behavior, but our behavior affects our cognition and our affective state, and vice versa. And so how could potentially social networks intervene in that system? And so that's the challenge. I mean, this requires models that account for the complex interactions between these factors in the context of social networks. Fortunately, though, the same social networks and social media that might be implicated in this rather dark trend are also furnishing the kind of data that might allow us to get a bit better picture of what's going on. And so my team and I have been, for the past decade, have focused on analyzing social media data to conduct what we would label computational social science, namely that we attempt to track the mental health status of millions of individuals from their social media activities, from the social media content that they post longitudinally over time, to see whether we can learn something about what's happening in these social networks that might, again, be implicated in these decreases of well-being that we're finding. Okay, so I'll present a few vignettes, a few results of or outcomes of this research. So, network effects of social media use and well-being, and this is again goes towards another one of those paradoxes which has been very well known in social network analytics. So, first, here's an analysis that we've done, and again, think of the kind of experiments that psychologists usually conduct over like 20 or 30 people, or perhaps a couple of hundred people at the most. Here we're talking about like tens of million people, or in some of our research, hundreds of millions of people. So this is based on a data set that we obtained in 2008, 2009, quite a while ago, for 5 million users, and we collected about 130 million of their tweets, and then retrieved their follow relationships. And we made a very basic assumption here, namely that if I follow you, you follow me back, then it's likely that we have some form of social relationship. I know that it's a little bit of a reduction, and social relationships are much more complex, but from the data, that's what we could gather. So if we have a reciprocal follow relation, we presume there's some social relationship between the two individuals, which means that for those 5 million users, we could essentially construct a social network. And there's a sample of the network shown on the right-hand side that is clearly indicative of the things that you would expect from a complex network. So high clustering degree, very skewed degree distributions, etc. Now, the next thing that we did for each of the individuals in that network, for each of those 5 million individuals, we downloaded their timeline, all of the tweets that they had posted up to that point in time. and then we subjected those tweets to a natural language processing technique called sentiment analysis. These are algorithms that essentially read text and then score them or grade them in terms of the affect that they express, the sort of semantic polarity, whether they're positive or negative tweets. That allowed us for each of those 5 million individuals to determine from the set of tweets that we downloaded whether overall they post tweets that were indicative of a positive or a negative affective state. Anyway, I won't go into the mathematics of this. And so here's what we found, and these are pretty surprising results because it shows that mood is assortative in these social networks. That means that people who post a lot of happy tweets and are presumably happy themselves prefer to connect to other happy individuals, right? So that's not quite so surprising, but what's really surprising is the very strong connection between people who overall post very negative content. And I give you some examples, but these are very negative users they post tweets that are indicative of serious affective issues. And these individuals tend to also connect predominantly to people with a similar negative mood state as themselves. So it's like misery loves company. So if you're miserable, and you connect to people on Twitter, you're more likely to connect to other miserable people. If you're happy, you're more likely to connect to other happy people. So, well, that's interesting, of course, because that means that that we choose our own social environments on these social media platforms in a way that might be not conducive to our well-being. So that's part of the puzzle, I think. But here's something else that is a known phenomenon in social networks, namely the friendship paradox. The friendship paradox, in a few words, is the finding that your friends, on average, have more friends than you do. Hashtag for real. And so it's a paradox, right? So this is a little bit like Lake Woebegone, where all of the kids are above average, So how is that possible? How is it possible that in social networks, your friends, on average, have more friends than you do? It sounds like a paradox. Well, the reason for that is these very skewed degree distributions. And so there's an example at the bottom of this slide where if you look at the blue circle, let's just say that's an individual, that individual has 6 connections. So this is one of these popular kids in school, right? While the other nodes, the red nodes have 2 or 3 connections, much fewer, right? So if each of those nodes, which is connected to the node in the blue, looks at the average connectedness of the average number of friends of their friends, that average will be higher than their own number of friends. So their friends on average will be more popular than they are. Why? Because of these very skewed degree distributions. Make sense? It's not really a paradox once you look at it, but it is a sort of a counterintuitive finding. So, okay, well, how about that happiness? How about that happiness assortativity we discovered where happy Twitter users connect to other happy Twitter users and unhappy Twitter users connect to other unhappy Twitter users. Well, how does that work then? Well, how does that interact? Well, if happiness and popularity are correlated, any feature correlated with popularity, right, which is distributed in a very skewed manner, will also be more prevalent in the neighbors of these nodes, right? So if in these social networks, your friends on average are more popular than you are, if popularity and happiness are associated, that means that your friends on average will also be happier than you are. Make sense? Okay, so is that actually the case? Well, let's see whether, in addition to a friendship paradox, we also find a happiness paradox. And again, this is contingent on popularity and happiness being correlated. Okay, so let's look at it. First of all, this is the Twitter network that we just talked about. We find a very strong popularity or friendship paradox. Again, your friends on average are much more popular than you are because there's a bunch of, a few very popular individuals, and they skew these distributions for all of us. And this is an effect that we all experience when we go in these social networks. We look around, and these very popular individuals, they kind of ruin it for all of us. Right, because they skew our perception of how popular people are in general. So for both the happy and for both groups, the happy people connected to happy people, unhappy people connected to unhappy people, we find a very strong popularity paradox. So that's bad news. But the worst news is that we also find a happiness paradox. And what that means is that the global picture here is that if you're miserable, you're unhappy, you're quite likely to connect to other unhappy users on Twitter. But those unhappy users on Twitter that you connect to, on average, will still be more popular and happier than you are. So this is almost unavoidable in these social networks. So you can easily see if you're not a very happy disposition, and you go in these social networks, you'll be connected to people who are certainly equally miserable as you are, but on average they will seem more popular and still happier than you are. So that's not a good situation at all, if you think about it, right? So this shows that with this kind of large-scale analysis of both the social relationships that we maintain on these social media platforms and some smart natural language processing, we can learn something quite fundamental about how these online social networks might actually induce the kind of effects that we talk about. I mean, this is almost impossible to avoid because all social networks that we know have these very skewed degree distributions, have these very skewed distributions of popularity. Right? And with these effects, these homophilic effects, we will find these very strong happiness and popularity paradoxes. So that's not great. But again, the unhappy group is worse off compared to the overall population, which is really bad. So this led us to, of course, this is sort of a statistical, this is an association that we can determine, but we're also quite interested in modeling the dynamics of human emotions at much smaller, much tighter scales than we had been capable of doing before. Now, measuring fluctuations in human affective states is really difficult because it's introspective. You essentially have to ask people how they feel. And you can't ask them how they feel too often, right? Because otherwise the question itself will warp people's mood states. I mean, if someone would ask me every 5 minutes how I'm feeling, I would get really cranky. And so it would affect my mood state and the measurement might become relatively invalid. So this is a typical conundrum in the social sciences and in psychology. Also, these introspective self-reports, you know, they suffer a little bit from social conformity. If you ask an American how they're doing, they're always doing great, right? So, but that's not a very reliable measurement of their emotional state. That's just a social expectation. So we attempted to actually leverage the same data that I showed you, well, the same Twitter data, to see whether we can actually measure the dynamics of naturally occurring emotions and actually follow how an individual emotional state fluctuates over time. And so what we did is the following. So let's see, I'm just going to skip through these slides. So we did the following. So we looked for tweets where someone said, I feel, and then a description of how they feel. Like, I feel good, I feel happy, I feel sad, I feel terrible, I feel awesome. So we looked for positive and negative adjectives or adverbs that followed the I feel statement. So that allowed us to split these individuals into two cohorts, two groups. People that said that they were feeling good, people that said that they were feeling bad. So they were having a positive or a negative emotion. And then we looked at the tweets posted before and after people indicated they were experiencing that emotion. Then those tweets were subjected to a sentiment analysis tool. This is, again, where the computers actually read these tweets and then determine whether those tweets were indicative of a positive or a negative mood, which then allowed us to chart the course of the individual's emotions before and after they reported explicitly that they were having an emotion. Right? Of course, this presumes that there's any effect. So if I say, for example, at time t, I give an indication that I'm feeling very happy, that doesn't mean that the tweets that I post 5 minutes before or 10 minutes before are any happier or any more negative than at that point in time, right? So that's essentially what we're trying to find out here by looking at changes in the mood state of these individuals before and after they explicitly report experiencing a mood. And so I won't go into the methods too much here, except that we looked at these what we call affect labeling tweets. Tweets that literally posted, I'm feeling, and then good, happy, great, and awesome, or negative, bad, unhappy, sad, terrible, horrible, and awful. People really do post those kind of tweets. We found 110,000 individuals, which is a sizable sample. Again, think of the scale compared to regular sort of psychological research. 110,000 individuals, of which 67,000, which is already somewhat of an indication that, you know, Twitter is in this sort of happy space that we all want to believe it is. So 67,000 individuals of those 110,000 indicated experiencing a negative emotion, 42,000 indicated experiencing a positive emotion. And again, what we then did, we looked at the 6 hours before and the 6 hours after they posted that tweet, and we analyzed the tweets that they posted in that interval, right? And we analyzed those tweets by the minute in terms of the the time span before and after they posted that affect labeling tweet. And then we use the Vader tool, which is a sentiment analysis tool that analyzes the tweet, but also takes into account negation, like I am not happy, everything sucks, you know, those kind of things. It even looks at emojis, exclamation points, etc. So typical online vernacular, and then makes an assessment of the valence of that tweet. And so here's what we found. And so this is one of the first results, I think, where we're able to actually chart the fluctuations of a naturally occurring, not an induced, not a sort of not an induced emotion at the minute scale. So you can see on the left-hand side, this is how we measured the fluctuations of a positive emotion as it was experienced and as it was sort of affecting the valence of the tweets that were posted before and after. See like a sort of a sharp run-up towards that the time at which someone reported having a positive emotion, and then a very quick decline back to the baseline right after people indicated that they were having a positive emotion. For the negative emotion, you can see like a slow ramp down that accelerates to sort of a nadir at 0 hour, which is the point in time where someone said that they were having a negative emotion, and then a very quick recovery almost immediately after. And that's sort of part of a little bit of a good news story about social media use and people talking about their emotions, because what this indicates is that a naturally occurring human emotion only lasts for about an hour or so, judging from the changes in the tweets. And the negative emotion also lasts about an hour, but is very quickly resolved when people actually express it online. So these results indicate that it's very useful to go on Twitter and let people know that you're having a negative emotion, because this is a known phenomenon in psychology that putting your emotions into words, a few words, not too many, actually helps to reduce the emotion. And that's what we're seeing in these results as well. We're seeing that the affect labeling actually helps people return to sort of a baseline very quickly in the case of the negative emotions in particular. So that's good news. Again, if you're having an emotion, just sit tight. Within an hour, you'll be back to your baseline. If you want to rush the process along a little bit, it really helps to tell people how you're feeling. So that's good. This also allows us to, of course, to model how these emotions fluctuate over time. And if you look at in the case of the negative emotion, there's some really interesting oscillations on that path. On that descent toward the nadir, where someone became aware of or reported having a negative emotion. But again, it's really interesting to see that when you express a negative emotion in a few words, very quickly people return to the baseline. So it's a very easy technique for emotional regulation that works very, very well and has also been proven out in other research. Well, that's interesting because that means that we can track the individual emotional state of millions of individuals, but of course we can also do that in the aggregate, for example, during a global pandemic. So here's an example of some work that we did where we looked at 20 US cities. The brown zones on the graph are when lockdowns were introduced, and you can clearly see the devastating effect of those lockdowns on the collective emotional state of individuals in these 20 US cities. I want to call out that you have to be very careful in how you conduct this kind of sentiment analysis. Because if we looked only at tweets that specifically mentioned COVID-19, then the results of our analysis would have indicated that people were happier because of COVID-19 and in particular because of the lockdowns. Why? Because in typical American fashion, people would be posting a tweet and something like, yeah, we can do this, everybody, let's beat the virus, which is an expression of a positive emotion, right? And so if you analyze only those tweets, you would come to the wrong conclusion that people are really happy about COVID-19 and the lockdowns. They're not. If you actually look at the tweets that don't mention COVID-19 of the same individuals in the same 20 cities, you'll see a very sharp decline from that baseline during these lockdowns, which indicates that these lockdowns were quite detrimental to sort of the public well-being. In fact, another research we showed that this effect is stronger for cities that have higher percentages of minorities. So these lockdowns actually led to sort of very inequitable outcomes in terms of public well-being. Okay, great. So, but you're probably thinking, I started this talk off by discussing the mental health status of our youth and how social media might be implicated in this. And so that of course calls for sort of a direct investigation of whether we can actually detect mood disorders or internalizing disorders, as we call them, for social media users from their affective dynamics, as I've just demonstrated. And that's something that we set out to do as well. I'm very happy, by the way, that the previous talk did a fantastic job of explaining sort of this notion of these complex systems and the equilibria that they can find themselves in, and this is sort of these landscapes of equilibria where these systems might be positioned in a stable basis of attraction, right? Where when they're disturbed, they have very high resilience. They return very quickly back to that set point, right? But when that landscape flattens out a little bit, then the system becomes more precarious, becomes less resilient. And just a little tip could easily push it into another basis of attraction, which could be quite pathological and quite dangerous. And so Martin Scheffer and Van der Limpert, close collaborators of mine at the University of Wageningen, have actually used this type of analysis to study the fluctuations in the emotional state of people suffering from depression. And the interesting thing is that if depression is a critical transition in the mood state of an individual, where their emotional equilibrium undergoes a critical transition towards another equilibrium state that is pathological, then it may be possible to detect the early warning signals for that critical transition. Because a system that is faced with sort of a flattening out of that landscape, right, will move slower. This is comparable to me when I stand on one leg, right, make lots of really quick fluctuations around that set point to keep myself upright on one leg, right. But let's just say I've had a few too many, been drinking a few beers, a little tired, right, and I might be about to fall over, you know, then I might start to sway more slowly. Right? And that's detectable. You can detect that in the autocorrelation and the variance of the system state over time. And so that might allow us to look at the fluctuations in the mood state of people that are about to make a transition to a depressed state and effectively have an early warning signal for the onset of depression. The problem with depression is, and then again, I was really happy that this was mentioned in the previous presentation, is that if this model applies to depression, it might also explain why it's so difficult to escape from a depressed state. We have good treatments for depression and anxiety that are quite reliable, but it takes a lot of effort once the system has actually dropped into that pathological state to get it back up to where it was before. It might even be impossible. And so that's why prevention is critical, and that's why these early warning signals are so important. And so what we did is we actually looked at Twitter users that, I mean, this happens, people do this for real. They go on Twitter and essentially, you know, post a tweet something like, I went to the doctor, turns out I've got major depression. Some people even post their prescription notes on Twitter. This happens, you know, I mean, this is public data, publicly available data that we can analyze and we can detect. And so in this analysis, what we did is we looked specifically for people on Twitter that instead of saying I feel bad or feel good, they said my doctor diagnosed me with depression. I went to the doctor and the doctor says I've got depression. And so once we detected that someone posted something like this, we downloaded all of their tweets. We harvested the individual's timeline, which meant that we could analyze their emotional state as it fluctuated from time step to time step in relation to the point in time at which they reported a diagnosis of depression. And that's very interesting because now we have these time series of their emotional state, and we can start to look for the early warning signals of the onset of the depression, namely whether the time series is exhibiting greater variance and higher autocorrelation over time, right before they drop into that pathological equilibrium. You might wonder, can we detect depression in online language? Yes, this has been demonstrated extensively. Actually, Eichstadt published in 2018, a year before the COVID-19 pandemic, published this fabulous paper where they actually showed that, yes, you can actually train a machine learning, a classifier, that looks at the language of individuals on Facebook, in this case, not Twitter, and it can actually predict their depression when you condition it on their medical records and actual official diagnosis. But Munmun Chudru actually did quite a bit of research using the same method as we did, where you look on Twitter, when someone says, I went to the doctor says I've got depression, and then you look at the language of these individuals over time, and you can train a classifier to predict whether or not they're depressed versus a control group. We did the same thing. Actually, a random forest classifier worked really well. We simply took the 300 best features, so the features are terms in this case, And that allowed a classifier with very high accuracy, suspiciously high accuracy, by the way, to predict whether someone was depressed or not. And so we looked at a few of the features that seem to have the highest predictive value. And as you could see, non-depressed individuals love meat and sex, and they also like laughing emojis. So those are features of people who are not depressed. Depressed individuals, on the other hand, as you can see, there's quite of course, we removed the tweets that specifically mention depression, but you can see that this is, these features have a lot of face validity, so to speak. That opens the really interesting possibility that we could be scanning the public Twitter feeds for millions of individuals and apply these classifiers to detect whether or not these individuals are either in danger of developing depression or have actually already developed depression. So that's a really interesting possibility. I should make a word of caution here, and the other researchers have warned about this as well, and I'm fully aware of this. Twitter is not the world's population. I mean, Twitter has about 400 million users. They may be quite atypical, and we're looking at a very small subset of those Twitter users that are depressed and that then reported a diagnosis on Twitter, etc. So I really have to warn a little bit that these data may not be fully representative. And we've seen recently some very interesting failures. And Luc Steels yesterday actually discussed this a little bit as well. These classifiers sometimes are very brittle. They tend to generalize poorly to data that I haven't seen before. For example, this is a use of neural networks to perform COVID-19 detection in chest X-rays, and when presented with pictures of cats, results were a little disastrous. So the classifier did not generalize well beyond the X-rays that it had been trained on. And that's dangerous. For example, here's another image recognition software that is capable of recognizing a Granny Schmidt apple. If you stick a note on it that says iPod, then it might be confused for an iPod by the same algorithm. So these algorithms don't have a lot of common sense, and so you have to be a little worried that in the case of detecting depression from social media feeds, they might be equally brittle. But that said, there's good reason to believe that this can be done. Okay, this is a little bit of a joke, but apparently a pigeon will also outperform some AI algorithms in detecting breast cancer in mammograms, because they've got very good vision. Okay, but anyway, so could we do this? Yes, I think we can. I mean, we've actually looked at individual timelines. Here's an example of an individual posting where we analyze the mood indicators from their tweets. And you can clearly, this is in the case of bipolar disorder, by the way, and you can clearly see some very sharp transitions happening when the individual goes into a manic versus a depressed state. And from the parameters of these time series, you may be able to predict, not only detect, but also predict when they're about to have a transition to this particular state. Am I running out of time? Slightly. Okay. Okay, so just give me 1 more minute, because I wanted to show you something which will really scare you, okay? Okay, good. So I'm going to move. So we can do this for millions of individuals, and we have, and the results have been quite promising. So we're hoping that we can make a contribution to not just the diagnostics, but also the detection of mental health disorders on social media. Okay, but last part, and just a few more slides, and I've abused your attention so far. Now, many of you might have actually been in a situation where you need to see a therapist for an internalizing disorder such as the depression. The golden standard for treatment right now is cognitive behavioral therapy. Cognitive behavioral therapy is based on this notion that I mentioned before, that this is called the cognitive triad, where our feelings shape our behavior and our thoughts shape our feelings and behavior, etc. So it's an interaction between these 3 components. Cognitive behavioral therapy spends a lot of time examining the thoughts that are implicated in the development and the onset and the maintenance of the depressed state. These thoughts very often are characterized by cognitive distortions, modes of thinking that are exaggerated, wrong, and overly negative with respect to oneself and the world. I could give you an example. Here's a few, for example, the evening will be a disaster. Like someone who's depressed might say something like, I won't go to the party because all of my friends hate me and I will have a bad time, it will be a disaster, and I'll go home crying, or something like that. You know, most of the time that means they won't go to the party, they won't get the positive reinforcement from their friends, right? So these thoughts have an actual effect on the behavior and motivation. Here's another example, no one will ever like me. So there's a distinct number of types that are distinguished in cognitive behavioral therapy. Of course, the first thing to do is, can we detect these in Twitter language? Can we detect these modes of thinking that are implicated in the development of the depression according to cognitive behavioral therapy in tweets? And so we looked at, we composed a lexicon of what we call cognitive distortion schemata, which are sort of 1, 2, 3, 4, or 5 grams that we can detect in tweets and that are markers of distorted thinking, of these cognitive distortions. There's 200, I saw someone trying to count them, there's 241 of these. And so, okay, so we look at we can now look at whether, you know, our depressed people on Twitter actually exhibit more of these markers than non-depressed people. So we did this for a random sample of about 10,000 individuals, 8,791 in a matched control group, a random sample, and 1,207 individuals in the depressed group. And what we found is, indeed, this is a long-standing hypothesis of cognitive behavioral therapy. The depressed individuals do actually exhibit very strongly the markers of distorted thinking. So the kind of sort of dichotomous, exaggerated, negative thinking that characterizes the depressed state. And that's really interesting because that means that in addition to the cognitive indicators of these internalizing disorders, the affective indicators, we can now also indicate the style of thinking that might be involved in depression. Okay, I'm rushing, so especially, by the way, personalizing and emotional reasoning. But I feel that it was a bad party, but I feel it wasn't good, even though it was good. So these are very prevalent. They're 2.5 times more prevalent in the depressed group versus the control group, in fact. But okay, so I'm rushing through this a little bit because I wanted to show you one thing. We just published this, I'll skip this as well. I apologize, I have too many slides. This is a paper we just published a year and a half ago in PNAS. And so what we did is we looked at Google Books. So this is English literature since the 1900s to the modern day, 2022. And for every year, we looked at the content of these books published, and we looked for the same markers of cognitive distortions. What are these markers? They don't mention they don't mention negative emotions. They don't mention depression. IMA, that's a labeling. Will never, catastrophic thinking. Yeah? And so what we found is, watch Germany, by the way. That's the green line. We see sort of an increase right before the Second World War, and then a big spike during the Second World War and right after, right? And then a return back to a baseline. For English, this is American English, so this applies to the US. We see a decline from 1900 to about the 1980s, where the markers of cognitive distortions in English, as it was written down in English literature, declined over time. But look what happens in the 1980s. It's like a hockey stick graph. You can clearly see a huge surge. This is like almost 2.5 standard deviations above the historical baseline of an increase of these cognitive distortions in 14 million books over 125 years. This is, I don't know what to think of this. Has our language become more conducive to the style of thinking, the mode of thinking that is implicated in the onset and the genesis of internalizing disorders such as depression and anxiety? It's not clear, but it is telling that some language shift occurred, and that language shift does match what we think we know about the language of individuals with depression and cognitive distortions. And now my question to you is, why? What's going on? What happened in the 1980s that we're seeing such a spike, 2 standard deviations above the historical mean of these cognitive distortions in languages? This applies to both German as well as Spanish. So this is a worldwide phenomenon. You can observe it across multiple cultures. I have to apologize to this audience. I haven't done it for French yet. French is a difficult case because of the double negation. The ne pas makes it really difficult to detect these cognitive distortions in language. So French was not included here, but if there's any suggestions on how to do this, I'd love to hear from you. Anyway, here's some papers that perhaps that show some more details about what I've been talking about. I want to sort of conclude my talk by saying that we live in a very precarious time, I think. We are not well. I think there's lots of indicators that our societies are increasingly under pressure. The stress levels are higher. The prevalence of internalizing disorders has increased among our youth to levels that I think are quite intolerable for a civilized society. We are besieged by the new communication technology, which may have various effects on our well-being and our ability to think, to feel, to communicate, to relate. And at the same time, we're having these amazing data at our disposition by virtue of the same environments that may be inducing these effects that will allow us to develop a much finer and much better understanding of the human psyche and what constitutes or the factors that drive well-being at a scale that essentially pertains to the entire global population. So I'll end here. I apologize for going over time, but I'd be willing to take questions and discuss further. Thank you.
Thank you, Johan, for this fascinating attempt to make sense of a very complex situation. Well, two remarks. The first one, thank you, because now I understand why all my friends are happier, more popular than me, yes, and so I'm not complex anymore. It's not only me. I thought it was only me. You are wonderful. And in fact, your talk reminded me of the old joke about the weather. They say, everybody is talking about the weather, but nobody is doing anything about it. You're talking about the social media. They make us very unhappy. In fact, what can we do about it? Should we ban it? Should we? No, we can't. What can we do about it?
I mean, most of this is observational, and what can we do about it? I mean, this is one of those wicked problems, and we talked about climate before, right? And so it's not just a complex problem; it's a wicked problem. I mean, these are for-profit environments. These are some of the richest companies in the world. They make their money by grabbing our attention, by any means possible. And the way they set up their business model is to implement these social networks, which we know to have these kind of effects. So what can we do about it? I mean, we believe in free enterprise, so the corporations are allowed to monetize these effects. But what can we do about it if it's, I compare this, some people have compared this, and I think that's not a horrible comparison, to smoking. I mean, I grew up in the 80s and 90s.
Bad habit, very bad habit.
It's a very bad habit, but it's also really disgusting. And so I have very little sympathy for it. But growing up in the 80s and 90s, smoking was everywhere. It was really difficult to ban it. It was really difficult to control it because the tobacco companies made their money by selling an addictive product that was damaging to our health. And so I think we're in a similar situation right now. So what to do about it? I mean, could we ban social media? I personally think we should restrict it to the greatest degree possible, and potentially even nationalizing some of these platforms. Sorry, there I said it. Sometimes
Well, you heard it
you have to
here first. It's kind of a French solution to a problem. Let's nationalize the whole thing, and maybe we'll solve.
Well, I'm happy to oblige.
Well, but there are also sometimes just individual solutions. Me personally, I'm not a member of any social media. I've never been a member of any social media. So there could be some individual solution. Anyway.
I deleted all of my social media accounts in 2016.
Wonderful.
Except Instagram, where I promote my DJ business. So.
Well, you have one social media more than me anyway. Thank you very much. As I said many times, we have brilliant thinkers at the UM6P in Mengere this week. They are here. You corner them somewhere, you can ask them their questions. Thank you very much, Johan. Thank you for our previous talk. And I think that Reda has an announcement to make regarding this beautiful campus that we have here. Please.
Yes, this message is addressed to the scientists who came from abroad and who are participating staying here during the whole week. Apparently, you didn't visit yet the campus, so we have organized a series of 3 visits. So you can, an email has been sent to you with the visit agenda, and until now we have only 1 person who registered. So please, there will be a visit organized this afternoon at 3 p.m. and then another one tomorrow at 11, Thursday at 11, and in the afternoon at 3. So if you have, if you stay here and you don't make the visit, you will miss most of what is done here in terms of scope, breadth, and depth, kind of city of knowledge. I've done myself the experiment. I've been here for 2 times and didn't do the visit. But once I did the visit, I realized really that something really emergent was taking place in Benguir. And this is why I'm calling Benguir the sinking plane, la plaine qui pense, because really we are on the start of a very interesting space. Thank you very much.
Thank you very much. A round of applause for Stuart KAUFFMAN, Ivar EKELAND, and Johan BOLLEN, our distinguished guests this morning. And let's have lunch. Thank you very much.